Right now, as you sit in your chair, breathing recycled air beneath a thin atmospheric shield, you are surrounded. Not by walls, not by the safety of gravity and magnetic fields you take for granted. You are surrounded by places so hostile, so fundamentally wrong, that they violate every assumption your biology makes about existence. Places where matter screams, where time shatters, where the laws of physics themselves begin to fail. These are not distant abstractions. You are falling toward them at 600 kilometers per second. The solar system drags you through a cosmic shooting gallery where every direction contains something that could erase you. Erase you from existence before your neurons could register the threat. And most of these killing grounds remain invisible to human eyes. Hidden behind wavelengths your retinas cannot process, lurking in the spaces between stars where darkness is not empty but alive with violence. The universe has built execution chambers on scales that dwarf comprehension, regions of space where reality operates under rules so alien that matter forgets how to be solid, zones where gravity becomes so savage that it tears apart the fundamental particles that compose your atoms, voids so absolute that they challenge the meaning of existence itself. And you are already inside one of them. Earth orbits a stable yellow star in a relatively quiet region of the Milky Way. This is what saves you. The cosmic real estate you occupy sits in a Goldilocks zone, not just around your sun, but within the galaxy itself. 50 light-years in any direction and you would be dead. 500 light-years and you would encounter phenomena that make death look like mercy. 5,000 light-years and you reach places where the concept of survival has no meaning. But that protection is temporary. The galaxy rotates, the solar system moves. And the universe has marked certain coordinates in space-time where horror becomes physics and physics becomes horror. Scientists have cataloged these locations, named them, measured their properties with instruments that barely survive the attempt. And what they discovered challenges the sanity of anyone who studies them for too long. This is not science fiction. Every location you will hear about in this video exists right now, burning or freezing or crushing, or dissolving matter according to mechanisms that operate at the limits of what the universe allows. Some of these places are as small as atoms. Others span distances that light cannot cross in the lifetime of civilizations. All of them share one property. They represent environments so extreme that they break the tools we use to understand reality. If you enjoy discovering what the cosmos keeps hidden in its darkest corners, hit that like button and subscribe. Because what you are about to hear will change how you see every star in the night sky. Those points of light are not peaceful. They are markers for cosmic abattoirs, operating in frequencies your eyes cannot detect. Prepare yourselves. We begin with the places that are close enough to threaten you. Then we descend into realms where distance becomes meaningless and terror becomes the fundamental force. The sun is not a gentle mother nurturing life on Earth. It is a fusion bomb detonating 400 trillion watts of power every second. Held together only by its own gravity pressing inward against the violence trying to tear it apart. And the most terrifying part is not the core where hydrogen nuclei slam together at 15 million degrees Celsius. The most terrifying part is the atmosphere. You learned in school that temperature decreases as you move away from a heat source. This is true for campfires, for ovens, for every thermal system that obeys the laws of thermodynamics. The sun violates this rule in a way that scientists still cannot fully explain. The visible surface of the sun, the photosphere, measures about 5,500 degrees Celsius, but move upward into the corona, the sun's outer atmosphere. And temperature spike to over 2 million degrees Celsius. The atmosphere is 360 times hotter than the surface beneath it. This should be impossible. Heat does not spontaneously flow from cooler regions to hotter regions without external energy input. Yet the corona blazes with temperatures that would vaporize any known material instantly, while floating above a comparatively cooler surface. The mechanism driving this thermal inversion remained mysterious until the Parker Solar Probe, launched in 2018, began its death-defying plunges into the corona itself. The probe discovered that the corona is not a passive gas cloud. It is a battlefield where magnetic field lines writhe and snap like whips made of pure force. The sun's interior acts as a giant dynamo, generating magnetic fields that thread through the photosphere and erupt into the corona. These field lines carry enormous amounts of energy, but they are not stable. They twist, they tangle. And when they reconnect in violent magnetic explosions, they release energy equivalent to millions of nuclear weapons detonating simultaneously. These explosions heat the corona to its absurd temperatures through a process called magnetic reconnection. Imagine two magnetic field lines being stretched like rubber bands until they snap. At the breaking point, the magnetic energy converts to heat and kinetic energy with 100% efficiency. Plasma particles in the reconnection zone are accelerated to near light speed in fractions of a second. The temperatures generated in these localized regions can exceed 10 million degrees Celsius. But the corona's extreme temperature is just the beginning of its horror. The sun's magnetic field does not contain the corona. Instead, it acts like a complex network of cages, some open and some closed. In regions where field lines form closed loops, plasma is trapped and heated to extreme temperatures. In regions where field lines open into interplanetary space, plasma streams outward as the solar wind, carrying the sun's violence directly toward Earth. The solar wind is not a breeze. It is a supersonic hurricane of charged particles traveling at speeds between 300 and 800 kilometers per second. At these velocities, a single proton carries kinetic energy sufficient to damage DNA if it reaches living cells. The continuous bombardment delivers approximately 1.5 times 10 to the power of 36 particles to Earth every single day. Most are deflected by Earth's magnetic field, but the pressure is relentless. During solar storms, the sun's violence escalates to apocalyptic levels. Coronal mass ejections, or CMEs, occur when the sun expels billions of tons of plasma and embedded magnetic fields into space. These eruptions happen because the magnetic field configuration becomes so unstable that entire sections of the corona simply explode outward. The fastest CMEs travel at over 3,000 kilometers per second, crossing the 150 million kilometer distance to Earth in less than 15 hours. When a CME impacts Earth's magnetosphere, the collision releases energy equivalent to thousands of nuclear weapons. The Earth's magnetic field does not provide perfect protection. It compresses on the sunward side and stretches into a long tail on the night side. During severe magnetic storms, the magnetosphere can be compressed to half its normal distance from Earth's surface. Satellites orbiting in the outer magnetosphere suddenly find themselves outside the protective boundary, exposed to the full fury of solar plasma. The Carrington event of 1859 remains the most powerful solar storm in recorded history. On September 1st of that year, British astronomer Richard Carrington observed a massive solar flare through his telescope. He sketched two patches of intensely bright white light that appeared suddenly on the sun's surface and persisted for approximately 5 minutes. 17 hours later, the associated CME struck Earth with such violence that auroras were visible as far south as the Caribbean. Telegraph systems, the cutting-edge technology of the era, failed across North America and Europe. Telegraph operators reported receiving electric shocks from their equipment. Some telegraph stations caught fire as the induced currents overwhelmed their systems. If the Carrington event occurred today, the economic damage would exceed $2 trillion, according to estimates by the National Academy of Sciences. The storm would induce electric currents in power transmission lines, overwhelming transformers not designed to handle such loads. The high-voltage transformers that form the backbone of electrical grids require months to years to manufacture and replace. A Carrington-class event would leave millions without electricity for extended periods, triggering cascading failures in water treatment, food distribution, and medical infrastructure. But the sun is capable of worse. Solar physicists have discovered evidence of superflares in the sun's past, events potentially 10 to 100 times more powerful than the Carrington event. The evidence comes from ice cores drilled from Greenland and Antarctica. Layers of ice corresponding to approximately 774 and 993 CE contain unusual spikes in radioactive isotopes like beryllium-10 and carbon-14. These isotopes form when cosmic rays strike Earth's atmosphere. The isotope spikes indicate that Earth was bombarded by massive fluxes of energetic particles during those years. The source was almost certainly the Sun experiencing superflare events. Tree ring data from ancient timber supports this conclusion, showing growth abnormalities during the same periods that correlate with radiation exposure. The frequency of such events appears to be roughly once every 1,000 years, meaning the next superflare is statistically overdue. A superflare would not just damage electrical infrastructure. The radiation dose at high altitudes would be lethal to aircraft passengers and crew during the event's peak. Astronauts in the International Space Station would receive radiation doses potentially sufficient to cause acute radiation sickness despite their shielding. Satellites would be disabled en masse as their electronics are fried by the particle bombardment. The GPS constellation, upon which modern civilization depends for everything from navigation to financial transactions synchronized by atomic clocks, would fail. The corona also produces solar energetic particle events, or SEPs, which occur during large flares and CMEs. These events accelerate protons and heavier ions to relativistic velocities, creating radiation storms that propagate through the solar system. SEPs arrive at Earth within minutes to hours after the initial flare, far faster than the CME itself. The fastest particles, traveling at significant fractions of light speed, can reach Earth in just 10 to 15 minutes. For astronauts on the Moon or Mars, SEP events represent a potentially lethal threat. On February 23, 1956, the Sun produced an SEP event so powerful that it is classified as a ground-level enhancement, meaning the particle flux was sufficient to be detected by neutron monitors at Earth's surface despite atmospheric shielding. An astronaut on the lunar surface during that event would have received a radiation dose of approximately 10 to 20 sieverts. 5 sieverts is considered an LD50 dose, meaning 50% lethality within 30 days. An astronaut in a simple spacecraft or habitat would have experienced severe radiation sickness and probable death. The physics governing the corona's behavior remains incompletely understood despite decades of study. The problem is that plasma physics at solar conditions involves coupling between electromagnetic forces, turbulence, gravity, and thermodynamics, operating across length scales spanning 9 orders of magnitude, from ion gyroradii measured in meters to coronal mass ejection spanning millions of kilometers. No computer simulation can resolve all of these scales simultaneously. Scientists have identified several mechanisms that likely contribute to coronal heating. Alpha waves, which are oscillations in the plasma threaded by magnetic field lines, can propagate from the photosphere into the corona and dissipate their energy as heat. Nanoflares, which are small magnetic reconnection events far too faint to observe individually but occurring millions of times per second, may collectively heat the corona through cumulative energy release. The actual mechanism probably involves all of these processes, plus others not yet identified. What makes the corona truly terrifying from a human perspective is that it extends far beyond the visible sun. The corona gradually transitions into the solar wind, which fills the entire heliosphere, a bubble approximately 100 astronomical units in diameter, or 100 times the Earth-Sun distance. This means Earth orbits inside the Sun's atmosphere. The planet is not separated from the Sun by empty space, but by different density regimes of the same magnetized plasma. During solar minimum, when the Sun's magnetic field is relatively organized and simple, the corona is structured into streamers extending from the equatorial regions and polar coronal holes where fast solar wind escapes. During solar maximum, the magnetic field becomes chaotic, and coronal holes can appear at any latitude. The entire corona becomes unstable, and the frequency of flares and CMEs increases dramatically. The Sun transitions from a relatively predictable neighbor to an erratic threat. You are inside the Sun's atmosphere right now. The solar wind particles flowing past Earth originated in the corona. The magnetic field embedded in those particles connects directly back to the sun's surface. When you see auroras dancing in the polar skies, you are watching solar plasma precipitating into Earth's atmosphere along magnetic field lines. The light you see is the signature of atmospheric gases being ionized by particles that left the corona just days earlier. The sun will exist in approximately its current state for another 5 billion years. But the corona's violence operates on human timescales. The next superflare could occur tomorrow or in 1,000 years. The next Carrington-class event could strike during your lifetime. And there is no way to prevent it. The sun's magnetic field operates according to its own chaotic dynamics, driven by convection patterns deep in the interior, that scientists cannot observe directly and cannot predict reliably more than a few days in advance. This is the furnace next door, a fusion reactor that has sustained nuclear detonations for 4.6 billion years. Wrapped in an atmosphere hotter than its own surface, periodically hurling billion-ton plasma bombs toward Earth at thousands of kilometers per second. The fact that Earth has survived inside this environment for geological timescales is not evidence of safety. It is evidence that extinction-level solar events are rare enough that life can recover between occurrences. There exists a class of object so magnetically violent that it warps the vacuum of space itself. A sphere 20 kilometers across that generates magnetic fields 10 quadrillion times stronger than Earth's. An object that, if placed halfway between Earth and the Moon, would erase every piece of magnetic data storage on the planet, would disrupt the molecular bonds in your body, would rip the electrons from your atoms through pure magnetic force. Magnetars are neutron stars on a cosmic steroid regimen. They represent what happens when stellar death goes beyond catastrophic, into the realm of physics that should not exist in nature. When a massive star exhausts its nuclear fuel, the core collapses in less than 1 second. Electrons are crushed into protons, forming neutrons. The core compresses to nuclear density, approximately 400 trillion times denser than water. A teaspoon of this material would weigh 4 billion tons on Earth. Most neutron stars spin rapidly and emit beams of radiation like cosmic lighthouses, earning the designation pulsars. But approximately 10% of neutron stars are born different. They are born with magnetic fields 1,000 times stronger than typical pulsars. These are the magnetars, and the term magnetic field fails to capture the violence they represent. The strongest magnetic fields created in terrestrial laboratories reach approximately 45 Tesla. The Large Hadron Collider uses superconducting magnets operating at 8.3 Tesla. To bend particle beams, these represent the pinnacle of human magnetic field generation. A magnetar's surface magnetic field strength reaches 10 to the power of 11 Tesla. 100 billion Tesla. The magnetic field at the magnetar's surface is 10 million times stronger than the strongest magnetic field ever created by humans. At field strengths above approximately 10 billion Tesla, quantum mechanics begins behaving strangely. The vacuum of space is not truly empty, but filled with virtual particle pairs that continuously pop into and out of existence. In normal space, these quantum fluctuations are symmetric and random. In the magnetar's field, they become polarized. The vacuum itself becomes birefringent, meaning light traveling parallel to the magnetic field moves at a different speed than light traveling perpendicular to it. This effect, called vacuum birefringence, was predicted by quantum electrodynamics in the 1930s, but remained experimentally unverified until observations of magnetars. When light from the magnetar passes through its own magnetic field, the polarization rotates in ways that can only be explained by quantum vacuum effects. The magnetar's field is so strong that empty space acquires optical properties similar to a crystal. But vacuum polarization is the least of the magnetar's weapons. The magnetic field contains energy in normal stars and planets. Magnetic field energy is negligible compared to gravitational or thermal energy. In magnetars, the magnetic field energy exceeds the binding energy of the star itself. The magnetar is held together not primarily by gravity, but by its own magnetic field. If you could somehow turn off the magnetic field, the star would explode. This magnetic dominance creates a stellar structure unlike anything else in the universe. The intense magnetic stress fractures the neutron star's crust like an eggshell. The solid surface, composed of iron nuclei, arranged in crystal lattice configurations more rigid than any terrestrial material, cannot withstand the magnetic pressure. It cracks, and when it cracks, the consequences propagate across light years. Magnetar flares rank among the most energetic explosive events in the universe. On December 27, 2004, magnetar SGR 1806-20, detected in the constellation Sagittarius, approximately 50,000 light-years from Earth, experienced what astronomers classify as a giant flare. The event began when a massive starquake ruptured the magnetar's crust. The fracture propagated through the surface in milliseconds, rearranging the magnetic field configuration in a catastrophic reorganization. The energy released in the first 0.2 of a second exceeded the total energy output of the Sun over 150,000 years. The initial gamma-ray burst struck Earth with such intensity that it ionized atoms in Earth's upper atmosphere, causing a sudden increase in electrical conductivity. The Very Large Array Radio Telescope detected the flare despite not being pointed toward the source. Ground-based instruments around the world were momentarily blinded by the radiation spike. If SGR 1806-20 had been located 10 light-years from Earth instead of 50,000, the flare would have delivered a gamma-ray dose sufficient to destroy the ozone layer. The atmosphere would have been bathed in radiation, equivalent to detonating thousands of nuclear weapons simultaneously in the stratosphere. The biosphere would have faced mass extinction, as the protective ozone barrier evaporated under the gamma-ray onslaught. Only 3 such giant flares have been observed in modern astronomical history: SGR 1806-20 in 2004, SGR 1900+14 in 1998, and SGR 0526-66 in 2004. The rarity of observations does not indicate rarity of occurrence. Magnetars exist throughout the Milky Way, most too distant or obscured to observe with current instruments. The galaxy likely experiences multiple giant flares per century. Most go undetected because they occur in directions where no instruments are watching, or in regions of space where intervening matter absorbs the radiation. The magnetar population in the Milky Way is estimated at approximately 30 million objects based on stellar evolution models. This represents roughly 1% of all neutron stars. Most magnetars transition to dormant states after 10,000 to 100,000 years as their magnetic fields gradually decay. But during their active phase, they represent some of the most dangerous objects in the galaxy. The physics of magnetar formation remains incompletely understood. Standard stellar collapse models predict neutron star magnetic fields approximately 1 trillion Tesla, far weaker than observed magnetar fields. Something during the collapse process amplifies the magnetic field by factors of 100 to 1,000. The leading theory invokes a dynamo mechanism operating during the first few seconds after the neutron star forms. During this period, the proto-neutron star is extremely hot, approximately 100 billion degrees Celsius. At these temperatures, neutrons can move with some fluidity, despite the extreme density. If the newborn neutron star rotates rapidly, perhaps once every millisecond, differential rotation between the core and outer layers can generate powerful electrical currents. These currents produce magnetic fields through the same dynamo process that generates Earth's magnetic field, but operating at energy scales 10 orders of magnitude higher. The dynamo process amplifies any pre-existing magnetic field from the progenitor star. Within seconds, the field strength can grow exponentially through positive feedback. The strong magnetic field extracts rotational energy from the spinning neutron star, causing it to slow down. The rotation energy converts to magnetic field energy. By the time the neutron star cools and solidifies, perhaps 10 to 100 seconds after formation, the magnetic field has been locked into the stellar structure at magnetar strengths. But magnetic fields of this intensity cannot remain static. The field lines threading through the star's interior and exterior are under enormous tension. Magnetic energy density exceeds 10 to the power of 25 joules per cubic meter in the magnetar's crust. This is energy density comparable to nuclear matter. The magnetic stress is so intense that it deforms the spherical shape of the neutron star, creating a slight oblateness. The star becomes an oblate spheroid, flattened at the poles and bulging at the equator. This deformation creates gravitational wave emission. The non-spherical mass distribution rotating in space generates ripples in spacetime that propagate outward at light speed. For typical neutron stars, this gravitational wave emission is negligible. For magnetars, the emission can be strong enough to be potentially detectable by next-generation gravitational wave observatories. The magnetar gradually loses rotational energy to both electromagnetic radiation and gravitational wave emission, spinning down over thousands of years. The magnetar's external environment is equally hostile. The intense magnetic field traps charged particles, creating a magnetosphere far more violent than anything in the solar system. Electrons and ions spiral along magnetic field lines, accelerating to relativistic velocities. When these particles strike the magnetar's surface, they generate X-rays and gamma rays. Through a process called synchrotron radiation, the magnetar glows in high-energy radiation, visible not to human eyes but to X-ray telescopes. The surface temperature of an active magnetar reaches 10 million degrees Celsius, far hotter than the surface of any normal star. This temperature results not from nuclear fusion, but from the slow decay of the magnetic field. As the field gradually weakens over millennia, the stored magnetic energy converts to heat. The magnetar is essentially a slowly cooling magnetic battery, dissipating 10 to the power of 31 watts of power, approximately the total luminosity of the sun. Despite having no internal energy source, approaching a magnetar would kill you through multiple mechanisms simultaneously. Beyond 10,000 kilometers, the magnetic field strength exceeds 1,000 Tesla. At this distance, the field would begin affecting your biology. Hemoglobin molecules in your blood contain iron atoms coordinated to protein structures. The magnetic field would attempt to align these molecules, creating sensations of discomfort and disorientation, similar to but far more intense than the effects reported by workers in high-field MRI machines. At 1,000 kilometers, the field strength reaches 1 million Tesla. The field would now be strong enough to affect atomic orbitals. Atoms are held together by electromagnetic forces between negatively charged electrons and positively charged nuclei. In normal circumstances, atoms are spherical or slightly elongated. In the magnetar's field, atoms become highly distorted, stretched into cigar shapes aligned with the field. The chemistry of your body would cease to function. A's molecular bonds distort beyond recognition. At 100 kilometers, you reach fields of 1 billion Tesla. Here, quantum mechanics breaks down entirely. The magnetic field energy becomes comparable to the electron rest mass energy. Virtual particle creation from the vacuum accelerates. The distinction between matter and field begins to blur. Your body, if it still existed as a coherent structure, would be interacting with a vacuum that has acquired the properties of matter. But you would never reach these distances. The radiation environment alone would be lethal far earlier. The magnetar emits X-rays and gamma rays with such intensity that the photon pressure would ablate any approaching matter. The surface flux of high-energy photons exceeds 10 to the power of 15 watts per square meter. At distances of 1,000 kilometers, for comparison, standing on the sun's surface subjects you to approximately 10 to the power of 8 watts per square meter. The magnetar's radiation environment is 10 million times more intense. The galaxy contains approximately 30 known magnetars, identified through their characteristic X-ray and gamma-ray emissions and their spin-down rates. Most are located in the galactic plane, concentrated toward the galactic center, where star formation rates are highest. The nearest confirmed magnetar, SGR 0526-66, is approximately 13,000 light-years from Earth. This distance provides comfortable safety. The inverse square law of radiation intensity ensures that magnetar flares, even giant flares, pose no threat at such distances. But the galaxy's star formation continues. Approximately 2 supernova explosions occur in the Milky Way per century. Roughly 1 in 10 of these might produce magnetars. The statistical probability of a magnetar forming within 100 light-years of Earth in the next million years is approximately 10%. Such an event would not pose an immediate existential threat, but it would increase the galactic background radiation in Earth's direction and potentially disrupt satellite operations during major flare events. The magnetar population extends beyond the Milky Way. Every galaxy with ongoing star formation produces magnetars at rates proportional to their supernova rates. The Andromeda Galaxy likely contains a similar magnetar population to the Milky Way. Starburst galaxies, where star formation proceeds at rates hundreds of times higher than in the Milky Way, might contain thousands of active magnetars simultaneously. The combined magnetic field energy from these populations could influence galaxy-scale dynamics in ways that remain unexplored. This is the magnetar nightmare. Stellar corpses that generate magnetic fields strong enough to break chemistry. Objects that make the vacuum of space optically active. Cosmic hand grenades that occasionally explode with enough energy to sterilize planetary systems across dozens of light-years. And they are scattered throughout the galaxy like landmines, invisible until they detonate. A black hole is not a hole. It is not empty space. It is not a tunnel to another universe or a portal to somewhere else. A black hole is an object so dense that it has collapsed past every quantum barrier that normally prevents matter from compressing infinitely. An object whose gravity is so extreme that it breaks time itself. And the boundary surrounding this object, the event horizon, is the most absolute border that exists in physics. The event horizon is not a physical surface. You could not touch it or bounce a ball off it. It is a mathematical boundary in space-time, beyond which the future light cone of any event points only inward. In normal space, if you emit a photon, it can travel in any outward direction. At the event horizon, even photons emitted directly upward fall back toward the center. The escape velocity equals the speed of light, and since nothing can travel faster than light, nothing can escape. This creates a profound asymmetry in causality. Events inside the event horizon cannot affect events outside it. Information cannot cross from inside to outside. But the reverse is not true. You can fall in. Matter and energy can cross the boundary inward with no resistance. The event horizon is a one-way membrane in space-time, and it violates every intuition humans have developed about boundaries and surfaces. The size of the event horizon depends only on the black hole's mass. The relationship is linear and precise. The Schwarzschild radius, the distance from the center to the event horizon for a non-rotating black hole, equals 2 times the gravitational constant times the mass divided by the speed of light squared. For a black hole with the mass of the Sun, the event horizon would have a radius of approximately 3 kilometers. For a black hole with 10 solar masses, the radius would be 30 kilometers. For a supermassive black hole containing 4 million solar masses like Sagittarius A star. At the Milky Way's center, the event horizon radius extends to approximately 12 million kilometers. But the event horizon is not where the horror begins. The horror begins much farther out, in a region called the ergosphere for rotating black holes. Or, more generally, in the zone where tidal forces become lethal. Tidal forces arise because gravity follows an inverse square law. The gravitational acceleration at your feet, if you fall feet first toward a black hole, is stronger than the acceleration at your head because your feet are closer to the source. For supermassive black holes, you could cross the event horizon alive and intact. The tidal forces at the event horizon of a billion solar mass black hole are actually quite mild. Approximately 1/10 of a meter per second squared per meter of body height. This is noticeable but not immediately lethal. You would feel a gentle stretching sensation. Your body would survive the crossing. But for stellar mass black holes, crossing the event horizon coincides with total structural failure of any physical object. Consider a 10 solar mass black hole. The event horizon radius is approximately 30 kilometers. The tidal acceleration at this distance is approximately 10,000 meters per second squared per meter of body height. If you are 2 meters tall, your feet experience approximately 20,000 meters per second squared more acceleration than your head. This is 2,000 times Earth's surface gravity, acting as a differential force trying to stretch you. The human body cannot withstand such forces. Bones break when subjected to accelerations exceeding approximately 50 times Earth gravity. Soft tissues rupture at lower thresholds. At 2,000 gravities of differential stress, your body does not merely break, it spaghettifies. The technical term used by relativists is tidal disruption. The process is exactly what it sounds like. You are pulled into a long, thin strand, like spaghetti. The spaghettification process does not occur instantaneously. It proceeds at rates determined by the tidal force gradient. For the 10 solar mass black hole, the stretching acceleration increases as you fall closer, by the time your feet are 10 kilometers from the singularity. Well, inside the event horizon, the differential acceleration exceeds 100,000 meters per second squared per meter. You are no longer recognizable as a human body. You are a stream of disconnected atoms stretched along a radial path toward the center. But you experience something even stranger than physical destruction. You experience time dilation. According to general relativity, gravitational fields slow down time. Clocks in strong gravitational fields tick more slowly than clocks in weak fields. This is not an illusion or measurement artifact. It is a real physical effect. Confirmed by atomic clocks on airplanes and satellites. Near a black hole, the time dilation becomes extreme. An outside observer watching you fall toward the event horizon would never see you cross it. As you approach the boundary, your clock appears to slow down. Your motion appears to slow down. The light from your body redshifts toward longer wavelengths, as photons lose energy climbing out of the gravitational well. You appear to freeze at the event horizon, your image becoming increasingly dimmed and redshifted until you fade from view entirely. To the outside observer, you take infinite time to reach the event horizon. But from your perspective, nothing special happens at the event horizon. You cross it in finite proper time, perhaps in seconds or minutes depending on your trajectory. You do not feel anything unusual at the moment of crossing. There is no warning, no barrier. You simply continue falling, accelerating inward under the relentless pull of gravity. Only later, as tidal forces intensify, do you realize what has happened. And by then, it is absolutely too late. You cannot send signals out. You cannot escape. You cannot even break. The interior of a black hole is not a place, it is a time. General relativity describes the interior geometry in coordinates, where the radial direction becomes time-like and the time direction becomes space-like. This mathematical description corresponds to a physical reality, where moving inward toward the singularity is as inevitable as moving forward in time. You cannot avoid reaching the singularity any more than you can avoid reaching next Tuesday. The singularity is in your future, not in a specific location. The singularity itself represents a breakdown in general relativity. At the singularity, curvature becomes infinite, density becomes infinite. The equations produce infinities that signal the theory has reached its limits. Physicists expect that quantum gravity effects, not yet described by a complete theory, become important at scales near the Planck length, approximately 10 to the power of -35 meters. At these scales, space-time itself becomes quantized and uncertain. But you would never perceive the quantum regime. The tidal forces destroy any coherent structure long before reaching Planck scales. By the time you are 1 meter from the singularity of a 10 solar mass black hole, the tidal acceleration exceeds 10 to the power of 15 meters per second squared per meter. This is acceleration equivalent to being hit by a particle beam in an accelerator. Your constituent atoms are ripped apart into nuclei and electrons. The nuclei themselves may be disrupted at closer approaches. The black hole does not merely destroy you, it erases the information about your existence. This statement generates controversy among theoretical physicists because it appears to violate quantum mechanics. Quantum theory demands that information is conserved. The quantum state of a system evolves according to unitary transformations that preserve information content. If you know the complete quantum state of the universe at one time, you can, in principle, calculate its state at any other time, forward or backward. But black holes seem to violate this principle. When matter falls into a black hole, it increases the black hole's mass. According to classical general relativity, the black hole is described completely by 3 parameters: mass, electric charge, and angular momentum. This is the no-hair theorem. Two black holes with identical mass, charge, and angular momentum are completely indistinguishable, regardless of what matter formed them or fell into them. All information about the specific quantum states of the infalling matter is lost. Stephen Hawking intensified this paradox in 1974 when he demonstrated that black holes emit thermal radiation due to quantum effects near the event horizon. Hawking radiation arises through quantum field theory in curved spacetime. Virtual particle pairs that spontaneously form near the event horizon can be separated by the intense gravitational field. One particle falls in, the other escapes as radiation. The escaping radiation carries energy away from the black hole, causing it to slowly evaporate. The radiation is purely thermal, characterized only by a temperature inversely proportional to the black hole's mass. For a solar mass black hole, the Hawking temperature is approximately 60 nanokelvins, far colder than the cosmic microwave background radiation temperature of 2.7 Kelvin. The black hole absorbs more energy from the surrounding universe than it emits through Hawking radiation, causing it to grow. But in principle, in a universe that has expanded and cooled sufficiently, black holes would eventually begin to evaporate. A solar mass black hole would require approximately 10 to the power of 67 years to evaporate completely through Hawking radiation. This timescale is incomprehensibly long, vastly exceeding the current age of the universe. Supermassive black holes would take even longer, but smaller black holes evaporate faster. A 1,000-kilogram black hole, if such objects exist, would evaporate in approximately 84 seconds, releasing energy equivalent to approximately 45 megatons of TNT. The black hole information paradox emerges when considering the complete evaporation process. If black holes evaporate completely, emitting only thermal radiation characterized by temperature alone, then any information about the quantum states of matter that fell in appears to be permanently lost. The final state is thermal radiation, which carries no information about initial states beyond total energy. Quantum mechanics is violated. The universe becomes fundamentally non-deterministic in a way that quantum theory forbids. Physicists have proposed numerous resolutions to this paradox. Some argue that information is encoded in subtle correlations in the Hawking radiation that become apparent only when analyzing the complete radiation output. Others propose that information is preserved in remnants left after black hole evaporation. Tiny Planck-scale objects that carry vast amounts of information. Still others suggest that the interior of a black hole is connected to other regions of space-time through wormholes, allowing information to escape through alternate paths. The most radical proposal involves the holographic principle, which suggests that all information about the interior of a black hole is encoded on its event horizon surface. The horizon area, measured in Planck areas, determines the maximum amount of information the black hole can contain. This principle has been extended to the universe itself, suggesting that our three-dimensional reality might be a projection of information encoded on a two-dimensional surface at the universe's boundary. These theoretical debates remain unresolved because testing them requires either observing black hole evaporation, which occurs on timescales exceeding the universe's age, or developing a complete theory of quantum gravity that unifies general relativity and quantum mechanics. Neither appears achievable with current technology or theoretical understanding. Meanwhile, black holes exist in profusion throughout the universe. The Milky Way alone contains approximately 100 million stellar mass black holes, remnants of massive stars that exhausted their nuclear fuel and collapsed. The galaxy also harbors one supermassive black hole at its center. Most other galaxies contain central supermassive black holes ranging from millions to billions of solar masses. The universe is thoroughly populated with these information-destroying objects. The nearest known black hole, Gaia BH1, is located approximately 1,500 light-years from Earth in the constellation Ophiuchus. It has approximately 10 solar masses and orbits in a binary system with a Sun-like star. The system is completely invisible to the naked eye and was discovered only through precise measurements of the companion star's motion. the black hole reveals itself through its gravitational influence, pulling the visible star into an elliptical orbit. This is the event horizon, a boundary that light cannot cross. A surface where time stops for distant observers but where nothing feels unusual to those who cross it. A one-way door in space-time leading to inevitable destruction. And potential information paradox. And the galaxy is filled with these objects, quietly orbiting, occasionally feeding, patient and eternal. Matter does not fall directly into a black hole. It spirals. And in that spiral, it transforms into the most violent plasma environment in the universe. The accretion disk surrounding a feeding black hole is not merely hot. It is a crucible where physics operates at extremes that obliterate chemistry, molecular bonds, and atomic structure itself. It is a place where matter is simultaneously compressed, heated, irradiated, and magnetically tortured before being consumed by the event horizon. Accretion disks form because infalling matter almost always has some angular momentum. Unless matter falls directly radially inward, which is statistically improbable, it enters orbit around the black hole. Conservation of angular momentum forces the matter into a rotating disk. As particles orbit, they collide with each other. These collisions dissipate kinetic energy as heat while transferring angular momentum outward. Matter in the inner disk loses angular momentum and spirals inward. Matter in the outer disk gains angular momentum and migrates outward. The disk becomes a rotating traffic jam where every particle is fighting to either escape or fall in. The friction generated by this process converts gravitational potential energy into thermal energy with terrifying efficiency. Approximately 40% of the rest mass energy of infalling matter can be converted to radiation in the accretion disk. For comparison, nuclear fusion converts approximately 0.7% of rest mass to energy. Accretion is 60 times more efficient than fusion, when 1 kilogram of matter falls into a black hole through an accretion disk. It releases energy equivalent to approximately 4 times 10 to the power of 17 joules. This is roughly 9 megatons of TNT from a single kilogram. The temperature of the accretion disk depends on the black hole's mass and the accretion rate. For a stellar mass black hole actively feeding, the inner accretion disk reaches temperatures of 100 million degrees Celsius. The disk does not emit visible light. It blazes in X-rays. The Wien displacement law of black-body radiation dictates that objects at these temperatures emit peak radiation in the X-ray band with photon energies measured in kilo-electron-volts. For supermassive black holes, the temperature scaling is different. The inner disk temperature is inversely proportional to black hole mass. A billion solar mass black hole has an inner disk temperature approximately 1 million times lower than a 10 solar mass black hole. The supermassive black hole's accretion disk peaks in ultraviolet and optical wavelengths. This is why quasars, which are supermassive black holes feeding voraciously during the early universe, appear as brilliant point sources of light rather than X-ray sources. But temperature tells only part of the story. The accretion disk is threaded with magnetic fields of extraordinary strength and complexity. These fields arise naturally through the magnetorotational instability, or MRI, discovered theoretically in 1991 by Stephen Balbus and John Hawley. The MRI operates in any differentially rotating plasma with weak magnetic fields. The differential rotation means that plasma in the inner disk orbits faster than plasma in the outer disk. When magnetic field lines connect plasma elements at different radii, the field lines act like springs. The inner, faster-moving plasma pulls the outer plasma forward, transferring angular momentum outward. Simultaneously, the outer plasma pulls the inner plasma backward, extracting angular momentum from the inner regions. This instability grows exponentially, amplifying weak seed magnetic fields into turbulent magnetic chaos within just a few orbital periods. The magnetic fields generated through MRI are not static. They are dynamic and turbulent, with field line reconnection events occurring continuously throughout the disk volume. These reconnection events release magnetic energy as kinetic energy, further heating the plasma and accelerating particles to relativistic velocities. The disk becomes a vast particle accelerator, naturally producing electrons, protons, and ions, traveling at significant fractions of light speed. The most spectacular manifestation of accretion disk physics is the relativistic jet. Not all accreting black holes produce jets, but those that do launch twin beams of plasma, perpendicular to the accretion disk plane, traveling at velocities exceeding 99% of light speed. These jets extend for thousands or millions of light-years into intergalactic space, carrying more energy than entire galaxies emit through stellar radiation. The mechanism powering jets remained mysterious until the 1970s when Roger Blandford and Roman Znajet proposed that rotating black holes could extract rotational energy through magnetic fields. The Blandford-Znajet mechanism operates through frame dragging, an effect predicted by general relativity where rotating masses drag spacetime itself into rotation. Near a spinning black hole, spacetime is dragged around the rotation axis. Magnetic field lines threading the event horizon are anchored in the rotating spacetime. As spacetime rotates, the field lines twist. The twisting magnetic fields accelerate charged particles from the accretion disk into highly collimated beams shooting outward along the rotation axis. The process extracts rotational energy from the black hole itself, converting it to kinetic energy in the jet. A maximally rotating supermassive black hole can power jets. With luminosities exceeding 10 to the power of 40 watts, which is approximately 1 trillion times the sun's luminosity, these jets are not passive flows. They are active, violent structures. Radio observations reveal that jets contain shocks, regions where supersonic plasma slams into slower-moving material or the ambient intergalactic medium. At these shock fronts, magnetic fields are compressed and amplified. Particles are accelerated through a process called diffusive shock acceleration, where particles bounce back and forth across the shock front, gaining energy with each crossing. The accelerated particles produce synchrotron radiation by spiraling around magnetic field lines at relativistic speeds. Synchrotron radiation from jets can span the entire electromagnetic spectrum from radio waves to gamma rays. The most energetic particles produce gamma rays through inverse Compton scattering, where the particles collide with low-energy photons and boost them to gamma-ray energies. The radiation environment within an active galactic nucleus, the region encompassing the black hole, accretion disk, and jets, is lethal on scales that beggar comprehension. The radiation flux near the inner accretion disk of a supermassive black hole actively accreting at 10% of the Eddington limit exceeds 10 to the power of 20 watts per square meter. This is 1 trillion times more intense than the radiation at Earth's distance from the Sun. Any matter exposed to such radiation fields would be photodisintegrated within microseconds. Photons carry sufficient energy to directly break apart atomic nuclei through photodisintegration, the reverse of nuclear fusion. The nuclei would fragment into protons, neutrons, and alpha particles. Even those fragments would be further ionized, stripped of any electrons by the intense radiation field. The accretion disk environment reduces all matter to a plasma of bare nuclei and free electrons. The innermost stable circular orbit, or ISCO, represents the closest distance where matter can orbit a black hole in a stable circular path. For a non-rotating black hole, the ISCO is located at 3 times the Schwarzschild radius, or 6 gravitational radii. For a maximally rotating black hole, the ISCO shrinks to approximately half the Schwarzschild radius. Inside the ISCO, no circular orbits exist. Matter must plunge directly toward the event horizon. At the ISCO, orbital velocities approach 50% of light speed. For non-rotating black holes, and even higher for rotating black holes. The plasma orbiting at these velocities experiences extreme time dilation and relativistic beaming effects. Photons emitted by the plasma have their frequencies dramatically shifted depending on emission direction. Photons emitted in the direction of motion are blue shifted to higher energies. Photons emitted opposite the motion are red shifted. This creates relativistic distortions in the appearance of the accretion disk. The approaching side of the disk appears much brighter than the receding side, even though both sides emit equal intrinsic luminosity. X-ray telescopes observe this relativistic beaming as a characteristic asymmetry in the X-ray emission from stellar mass black holes in binary systems. The effect provides direct observational evidence of plasma moving at relativistic velocities mere kilometers from event horizons. The accretion disk is not uniform. It exhibits variability on all timescales, from milliseconds to years. The millisecond variability arises from turbulent fluctuations in the innermost disk regions, where orbital periods are measured in milliseconds. Longer timescale variability results from changes in the mass accretion rate, possibly triggered by instabilities in the outer disk or variations in the supply of gas from companion stars in binary systems. X-ray binary systems, where a stellar mass black hole accretes matter from a companion star, exhibit dramatic outbursts called X-ray novae. This system can spend years in a low state, accreting matter slowly and accumulating material in the outer disk. When the accumulated mass exceeds a critical threshold, the disk suddenly becomes thermally unstable. A thermal runaway initiates in the outer disk and propagates inward as a heating wave. Within days, the accretion rate increases by factors of thousands, and the X-ray luminosity spikes to peak values approaching the Eddington limit. The Eddington limit represents the maximum luminosity an object can sustain through accretion before radiation pressure balances gravitational attraction. At the Eddington limit, photons streaming outward from the accretion disk exert enough radiation pressure on infalling matter to halt further infall. The Eddington luminosity depends only on mass, approximately 10 to the power of 31 watts per solar mass. A 10 solar mass black hole has an Eddington luminosity of approximately 10 to the power of 32 watts. Some accreting black holes exceed the Eddington limit temporarily during super-Eddington accretion episodes. During these phases, the inner disk becomes geometrically thick and optically opaque. The excess energy cannot escape efficiently through radiation. Instead, it drives powerful winds and outflows that eject matter from the system. The disk effectively self-regulates, preventing sustained super-Eddington accretion through mechanical feedback. The physics of accretion disks has been confirmed through multiple observational techniques. X-ray timing observations reveal quasi-periodic oscillations, or QPOs, in the X-ray emission from black hole binaries. These oscillations occur at frequencies corresponding to orbital periods at specific radii in the inner accretion disk. The highest frequency QPOs occur at hundreds or thousands of hertz, indicating orbital radii just a few gravitational radii from the black hole. Iron K-alpha X-ray emission lines provide another diagnostic of accretion disk physics. Iron atoms in the disk are ionized by X-rays from the hot inner disk. When iron ions recombine with electrons, they emit characteristic X-ray photons at 6.4 kilo-electron volts. But the emission line observed from accreting black holes is not a sharp peak. It is dramatically broadened and distorted into an asymmetric profile, extending from 4 to 7 kilo-electron volts. This distortion arises from relativistic effects. The extreme velocities of orbiting iron atoms produce Doppler shifts. The intense gravitational field produces gravitational redshift. The combination creates a characteristic line profile that encodes information about the disk geometry, black hole spin, and viewing angle. X-ray observatories like XMM Newton and NuSTAR routinely observe these relativistically broadened iron lines, providing direct probes of space-time geometry within 10 gravitational radii of black holes. The accretion disk environment destroys not only matter, but also concepts. The distinction between past and future becomes ambiguous. Time dilation means that different parts of the disk experience time at different rates. Causality becomes entangled. Light paths are bent so severely that you could orbit the black hole multiple times along photon orbits that circle at 1.5 Schwarzschild radii. Events can be connected by light paths that loop around the black hole before reaching distant observers. This is the accretion disk inferno, a region where 40% of matter's rest mass converts to radiation, where temperatures exceed 100 million degrees, where magnetic fields accelerate particles to light speed and launch jets across galactic distances, where space-time itself is twisted by rotation and gravity, into geometries that defy everyday intuition. It is a cosmic blast furnace operating at efficiencies that make stars look wasteful and nuclear weapons look feeble. The surface of a neutron star is the hardest material in the universe. Not metaphorically hard, not hard like diamond or tungsten carbide. Hard in a way that redefines the concept of solidity. The crust of a neutron star is composed of atomic nuclei packed so tightly that electrons are crushed into the nuclei themselves, transforming protons into neutrons. The resulting lattice structure has a tensile strength approximately 10 billion times stronger than steel. This is not a surface you could walk on. There is no walking at a location where gravity accelerates objects at 200 billion meters per second squared. For reference, Earth's surface gravity accelerates objects at 9.8 meters per second squared. The neutron star's surface gravity is approximately 20 billion times stronger. If you could somehow place your body on a neutron star's surface, you would be compressed to a layer approximately 1 atom thick in a fraction of a nanosecond. But the mechanical crushing is not the only threat. The neutron star's surface is hot. Temperatures range from 100,000 to 1 million degrees Celsius. For typical pulsars that have cooled for thousands to millions of years, newly formed neutron stars can have surface temperatures exceeding 10 million degrees Celsius. At these temperatures, the surface emits X-rays with photon energies measured in kilo-electron volts. The radiation flux would vaporize any approaching matter long before it could touch the surface. The magnetic field threading through the neutron star surface creates additional horror. Even non-magnetar neutron stars possess surface magnetic field strengths of approximately 100 million Tesla. This is 1,000 times stronger than the strongest fields produced in terrestrial laboratories. The field is strong enough to distort atomic structure, stretching electron orbitals into elongated cigar shapes aligned with the field lines. In this field strength regime, atoms behave according to rules that do not exist anywhere in the solar system. Quantum mechanics dictates that electrons occupy discrete energy levels around nuclei. But in strong magnetic fields, these energy levels split into multiple sublevels through the Zeeman effect. At 100 million Tesla, the Zeeman splitting becomes comparable to the binding energy of atoms. Chemistry ceases to function. Molecular bonds cannot form. Matter exists only as isolated ionized atoms with distorted electron clouds. The neutron star's rotation adds centrifugal force to the already extreme environment. Young pulsars rotate hundreds of times per second. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second. At the equator of this pulsar, the surface velocity reaches approximately 1/5 of light speed. This centrifugal acceleration partially cancels the gravitational acceleration, but the net acceleration still exceeds 100 billion meters per second squared. This rapid rotation creates a wind. The neutron star's magnetic field, frozen into the stellar surface and rotating with it, drags charged particles from the surface and accelerates them outward. These particles are ripped from the solid crust by the intense electric fields generated by the rotating magnetic field. The process is similar to how a rotating bar magnet in a conducting medium generates currents, but operating at energy scales that dwarf any terrestrial analog. The pulsar wind carries away rotational energy, causing the neutron star to gradually spin down over millions of years. Young pulsars lose rotational energy at rates exceeding 10 to the power of 38 watts, approximately 10 million times the sun's luminosity. This energy does not emerge as thermal radiation, but as the kinetic energy of relativistic particles streaming outward in the pulsar wind. The particles, primarily electrons and positrons, travel at velocities exceeding 99.9% of light speed. When this wind collides with surrounding material, either from a companion star or from the supernova remnant that formed the neutron star, it creates a pulsar wind nebula. The Crab Nebula represents the most studied example. The pulsar at the Crab's center, born in a supernova observed in 1054 CE, rotates 30 times per second and powers a nebula spanning 11 light-years. The nebula glows in all wavelengths from radio to gamma rays, powered entirely by the pulsar's rotational energy. The interior structure beneath the neutron star surface is even more alien, at depths of approximately 100 meters below the surface. The density reaches 10 to the A power of 14 grams per cc. At these densities, neutrons drip out of neutron-rich nuclei, creating a neutron fluid that permeates the lattice of nuclei. This region is called the neutron drip layer, marking the transition from solid crust to liquid neutron matter. Descending deeper at densities exceeding 4 × 10 to the power of 14 grams per cc, the nuclei dissolve entirely. The crust gives way to a uniform fluid of neutrons with a small admixture of protons and electrons. This is the neutron star outer core, a superfluid with properties unlike any terrestrial liquid. The neutrons form Cooper pairs, analogous to the electron pairs in superconductors, creating a quantum fluid with zero viscosity. The superfluid neutrons can sustain currents that persist indefinitely without dissipation. These quantum vortices thread through the neutron superfluid, carrying quantized units of angular momentum. When the neutron star spins down due to pulsar wind torque, the vortices must migrate outward through the superfluid to reduce the total angular momentum. But the vortices are pinned to the solid crust by nuclear forces. The crust and superfluid rotate at slightly different rates until the stress becomes too large. When the stress exceeds the pinning force, thousands of vortices suddenly unpin and migrate outward in an avalanche. The superfluid spins down suddenly, transferring angular momentum to the crust. The crust accelerates. External observers see this as a pulsar glitch, a sudden increase in rotation rate. The Vela pulsar experiences glitches approximately once every 3 years, where the rotation rate increases by approximately 10 microseconds per rotation period. Within days or weeks, the rotation rate returns to its pre-glitch trajectory as the crust and superfluid recouple. Deeper still, at densities exceeding 10 to the power of 15 grams per cc, the physics becomes speculative. This is the neutron star inner core, where densities approach or exceed nuclear saturation density. At these extreme conditions, neutrons might dissolve into their constituent quarks. The quarks, normally confined within individual neutrons, could become deconfined and form a quark-gluon plasma permeating the entire core. Theoretical models predict the possible existence of strange quark matter in neutron star cores. Normal matter consists of up and down quarks arranged in protons and neutrons. But at high densities, it might be energetically favorable for some up and down quarks to transform into strange quarks through weak interactions. Strange quark matter could be absolutely stable, more stable even than normal nuclear matter like iron. If strange quark matter exists in neutron star cores, it might not remain confined there, a controversial hypothesis called the strange matter hypothesis proposes that strange quark matter might be the true ground state of matter at all densities, not just ultra-high densities. Normal matter like atoms would be metastable, unstable but long-lived due to an energy barrier preventing conversion to strange matter. The terrifying implication is that contact with a seed of strange matter could trigger a conversion reaction, a single strangelet, a nugget of strange quark matter. Contacting normal matter could catalyze the conversion of nucleons into strange quarks. The reaction would release energy and propagate through all adjacent normal matter. The conversion front would advance at near light speed, transforming everything it touches into strange matter. If a neutron star containing a strange matter core were disrupted, perhaps during a merger with another neutron star, strange matter could be ejected into space as strangelets. These strangelets would be denser than normal matter, sinking through planetary interiors if they struck a planet. Earth passing through a cloud of strangelets left over from a neutron star merger could trigger a conversion reaction that transforms the entire planet into a ball of strange matter within seconds. The probability of such an event is considered extremely low by most physicists, but the hypothesis remains unrefuted. The universe has existed for 13.8 billion years. In that time, countless neutron star mergers have occurred throughout the observable universe. If strange matter strangelets are stable and have been produced, they now populate the interstellar medium at some low density. Every second, Earth is potentially being traversed by strangelets too small to trigger conversion or passing through regions of space that contain no strangelets. Neutron star surfaces also host nuclear processes that do not occur anywhere else. When a neutron star in a binary system accretes hydrogen and helium from a companion star, The material accumulates in a thin layer on the neutron star surface. The extreme gravity compresses this layer, heating it and increasing its density. Eventually, conditions become suitable for nuclear fusion, but fusion under neutron star gravity operates differently than in stellar cores. The fusion ignites suddenly and explosively across the entire neutron star surface in a thermonuclear runaway called a Type 1 X-ray burst. The accumulated fuel burns within seconds, releasing energy equivalent to 100,000 times the sun's luminosity over 10 to 100 seconds. The surface temperature spikes to 50 million degrees Celsius. The X-ray flux increases by factors of thousands. Then the burst ends. The surface cools, and the cycle begins again as fresh material accretes. Some neutron stars experience superbursts, rare events where carbon accumulated through helium burning in previous bursts ignites in a deeper layer. Superbursts release 10,000 times more energy than normal X-ray bursts and can last for hours. The mechanism triggering superbursts remains debated, but they demonstrate that neutron star surfaces host fusion processes operating under conditions that terrestrial fusion experiments cannot replicate. The combination of gravity, magnetic fields, temperature, and nuclear reactions makes the neutron star surface the most hostile solid surface in the known universe. No material from the periodic table could exist there in its normal state. No spacecraft material could withstand even proximity to such an object. The radiation field alone would destroy electronics through ionization damage. The magnetic field would induce massive currents in any conducting structure, melting it within milliseconds. Approaching a neutron star from a distance of 1,000 kilometers, well before any surface contact, the tidal forces would exceed human tolerance. The magnetic field would reach 1 million Tesla, enough to disrupt chemical reactions in biological tissues. The X-ray flux would deliver a lethal radiation dose within seconds. At 100 kilometers, the tidal forces would tear apart molecular structures. At 10 kilometers, atomic structures would begin to fail. The closest humans have come to a neutron star is purely observational, through photons that travel thousands of light years across space. X-ray telescopes like Chandra, XMM Newton, and NuSTAR observe neutron stars by detecting X-rays emitted from their surfaces and magnetospheres. Radio telescopes detect the beamed radio emission from pulsars as their magnetic poles sweep past Earth like cosmic lighthouses. Gravitational wave detectors like LIGO and Virgo detect the space-time ripples created when neutron stars spiral together and merge. The neutron star merger detected on August 17, 2017, designated GW170817, provided the first direct observation of two neutron stars colliding. The gravitational wave signal lasted approximately 100 seconds as the stars orbited faster and faster before merging. The merger created a kilonova, an explosion powered by the radioactive decay of heavy elements synthesized during the collision. The event also produced a gamma-ray burst detected by the Fermi Gamma Ray Space Telescope. Just 1.7 seconds after the gravitational wave signal ended, this observation confirmed that neutron star mergers produce heavy elements like gold and platinum through rapid neutron capture nucleosynthesis. The extreme neutron density during the merger creates conditions where atomic nuclei can capture many neutrons in rapid succession. Before undergoing beta decay, this R-process nucleosynthesis produces approximately half of all elements heavier than iron in the universe. The gold in your jewelry was likely forged during a neutron star merger somewhere in the galaxy billions of years ago. This is the neutron star surface, a solid crust of degenerate matter stronger than any substance humans have conceived. A surface where gravity is so strong that time itself runs slower, where magnetic fields reshape quantum mechanics, where nuclear fusion proceeds as explosive bursts rather than steady reactions, where the boundary between solid and liquid is enforced by pressures that exceed the structural limits of all normal matter. It is a place that defines the ultimate limits of material strength and density before matter collapses into black holes. For approximately 10 seconds, an event in a distant galaxy releases more energy than the Sun will emit during its entire 10 billion-year lifetime. The energy emerges not as a spherical explosion radiating in all directions, but as twin beams of radiation so concentrated that they burn through space, like cosmic cutting torches. These beams carry gamma rays, the most energetic form of electromagnetic radiation, traveling at light speed across billions of light years. And if one of these beams happens to intersect Earth, the biosphere dies. Gamma-ray bursts, or GRBs, are the brightest electromagnetic events in the universe. They were discovered accidentally in 1967 by the Vela satellites. Bidicam military spacecraft designed to detect Soviet nuclear weapons tests in space. The satellites detected sudden flashes of gamma rays coming from space rather than Earth. The discovery remained classified until 1973 when the data was finally published. The scientific community was baffled. Nothing in theoretical astrophysics predicted such intense, brief gamma-ray sources. The mystery deepened over decades. Gamma-ray bursts occurred randomly across the sky with no concentration toward the galactic plane or galactic center. This suggested an extragalactic origin. But the energy requirements for extragalactic sources seemed impossible. If GRBs originated in distant galaxies billions of light years away, their intrinsic luminosity would have to exceed 10 to the power of 51 watts. This is the entire energy budget of a supernova explosion released in seconds rather than weeks. The solution came in 1997 when the Beppo SAX satellite obtained the first precise position of a GRB afterglow. Ground-based telescopes quickly identified the optical counterpart. In a distant galaxy approximately 6 billion light-years from Earth, the distance confirmed that GRBs are indeed extragalactic and extraordinarily luminous. But it also revealed something crucial. The gamma rays are not emitted isotropically. They emerge in narrow jets with opening angles of only a few degrees. Relativistic beaming concentrates the emission into these jets. Instead of the energy spreading over an entire sphere, it emerges in two cones like beams from cosmic searchlights. This reduces the total energy requirement by factors of hundreds or thousands, while maintaining the observed brightness. An observer within the beam sees an extremely bright burst. Observers outside the beam see nothing. We detect only those GRBs whose jets happen to point toward Earth. The statistics are terrifying. Astronomers detect approximately 1 gamma-ray burst per day using satellites like the Fermi Gamma Ray Space Telescope and the Swift Observatory. These are only the bursts, whose jets point toward Earth. If the typical jet opening angle is approximately 5 degrees, then the true rate of GRB events is approximately 300 times higher. This means roughly 300 gamma-ray bursts occur somewhere in the observable universe every single day. Most go undetected because their jets point in other directions. Gamma-ray bursts are divided into two classes based on duration. Short GRBs last less than 2 seconds and arise from neutron star mergers, the same events that produce gravitational waves and kilonovae. Long GRBs last from 2 seconds to several minutes and are associated with the deaths of very massive stars, those exceeding approximately 30 solar masses. These stars collapse directly to black holes while simultaneously launching relativistic jets through their own outer layers. The long GRB scenario is called a collapsar. When the core of a massive star collapses, it forms a rapidly rotating black hole surrounded by a thick accretion disk. Fed by infalling stellar material. The black hole and accretion disk system taps into the immense gravitational potential energy of the collapse. Through the Blandford-Znajek mechanism and other jet launching processes, twin jets are accelerated to velocities exceeding 99.99% of light speed. These jets drill through the star's envelope, emerging into space within seconds. The jet material is not solid, but ultra-relativistic plasma, with bulk Lorentz factors exceeding 100. Lorentz factor of 100 means that time passes 100 times slower for the jet plasma than for stationary observers. A process lasting 1 second in the jet's rest frame appears to last 100 seconds to external observers. The jets carry magnetic fields wound into complex helical configurations. As the plasma travels outward, internal shocks develop, where faster-moving material overtakes slower-moving material. These shocks accelerate electrons to extreme energies through diffusive shock acceleration. The electrons then spiral around magnetic field lines, emitting synchrotron radiation. For electrons accelerated to Lorentz factors exceeding 1 million, the synchrotron radiation emerges as gamma rays. The gamma-ray photons themselves carry energies measured in mega-electron volts, or MeV. A single photon can have energy equivalent to the rest mass of an electron. These are not the gentle photons of visible light with energies of a few electron volts. Gamma-ray photons are particles of pure energy capable of initiating nuclear reactions, breaking apart atomic nuclei, and creating electron-positron pairs directly from the vacuum through pair production. The total energy budget of a long gamma-ray burst is approximately 10 to the power of 44 joules, equivalent to converting approximately 10% of a solar mass into pure energy. This energy emerges within 10 to 100 seconds. The peak luminosity reaches 10 to the power of 51 watts, briefly outshining all the stars and all the galaxies in the observable universe combined. For those few seconds, a single dying star produces more electromagnetic energy than 100 billion galaxies. But the prompt gamma-ray emission is only the beginning. As the relativistic jet plows through the circumstellar medium, the material shed by the progenitor star during its lifetime. It drives a forward shock into this material and a reverse shock back into the jet itself. These shocks heat the plasma and accelerate more particles, producing afterglow emission that persists for days to weeks at X-ray and optical wavelengths. The afterglow provides the mechanism for studying GRB host galaxies. Within hours of a GRB detection, ground-based telescopes can observe the fading optical afterglow and obtain spectra. These spectra reveal the redshift of the host galaxy, allowing astronomers to determine the distance and therefore the intrinsic luminosity. They also show absorption lines from the interstellar medium of the host galaxy, providing information about its chemical composition and structure. Long gamma-ray bursts preferentially occur in low metallicity, low-mass galaxies with high star formation rates. These are galaxies similar to what the Milky Way might have resembled 10 billion years ago during the epoch of peak star formation in the universe. The low metallicity is crucial because massive stars in metal-rich environments lose too much mass through stellar winds before they can collapse. Only in metal-poor environments can stars retain enough mass and angular momentum to form the rapidly rotating black holes that power GRB jets. The detection of GRB 980425, observed on April 25, 1998, provided the first clear evidence for the supernova connection. The optical afterglow brightened unexpectedly approximately 2 weeks after the burst. Spectroscopy revealed that this late-time brightening was a supernova, designated SN 1998BW. The supernova spectrum showed broad features indicating material moving at velocities exceeding 30,000 kilometers per second, much faster than typical supernovae. This hypernova was powered by the same collapse that launched the GRB jet. The beaming of gamma-ray bursts creates selection effects in what we observe. We detect preferentially those bursts that point directly at us. For an observer within the beam, the combination of relativistic motion and beaming creates extreme amplification of the emission. But the flip side is equally important. For observers outside the beam, the GRB is essentially invisible. The supernova explosion occurs, visible to all directions, but the gamma rays emerge only within the narrow jet cones. This means that the Milky Way likely contains the remnants of past collapsers where the jets pointed in directions away from Earth. These events produce supernovae that astronomers might have observed centuries or millennia ago, never knowing that relativistic jets were simultaneously propagating through space in other directions. Historical supernovae like the one observed in 1054 CE that created the Crab Nebula might have been GRBs with jets pointed away from Earth. The threat posed by gamma-ray bursts to life on Earth depends critically on distance. The gamma rays from a GRB interact with Earth's atmosphere, stripping electrons from nitrogen and oxygen molecules and creating nitrogen oxides. These nitrogen oxides catalytically destroy ozone through well-understood chemical reactions. Ozone in the stratosphere protects the surface from solar ultraviolet radiation. Ozone depletion would increase UV flux at the surface. damaging or killing organisms and disrupting photosynthesis in plants and phytoplankton. Computer simulations indicate that a long gamma-ray burst occurring within 3,000 light-years of Earth, with its jet pointed directly at us, would deplete 50% of the ozone layer. The depletion would persist for years as stratospheric chemistry slowly regenerates ozone. During this period, surface UV levels would increase by factors of 2 to 3. The biological impact would be severe. Phytoplankton, which form the base of oceanic food chains and produce approximately half of Earth's oxygen, are extremely sensitive to UV radiation. The statistical probability of such an event depends on the GRB rate in the Milky Way and the jet orientation probability. The Milky Way likely experiences one long GRB per few 100,000 years, with typical jet opening angles of 5 degrees. The probability that a Milky Way GRB points toward Earth is approximately 1 in 1,000. Combined, this suggests a lethal GRB event approximately once every few 100 million years. This rate is sufficient to have affected Earth's biosphere during its 4.5 billion year history. Some paleontologists have proposed that the Ordovician mass extinction 445 million years ago, which eliminated approximately 85% of marine species, might have been triggered by a GRB. The extinction occurred in 2 pulses, separated by several 100,000 years. The first pulse shows characteristics consistent with global cooling, possibly from altered atmospheric chemistry. The second pulse shows evidence of increased UV radiation exposure, exactly what would be expected from ozone layer depletion. The evidence remains circumstantial. No smoking gun proves a GRB caused the Ordovician extinction, but the hypothesis is testable through geological proxies. Certain isotope ratios in sedimentary rocks from the extinction boundary could reveal atmospheric chemistry changes consistent with nitrogen oxide production from GRB gamma rays. Spore preservation patterns might show UV damage signatures. The hypothesis remains active in the paleontological literature. More recently, GRB research has focused on the highest energy gamma rays detected from some bursts. The Fermi Large Area Telescope has detected photons with energies exceeding 100 giga-electron volts, or GeV, from several GRBs. These ultra-high energy photons challenge theoretical models because they should be absorbed through pair production when interacting with the X-ray and optical photons produced in the same burst. The detection of GeV photons, arriving hours after the burst onset, suggests that either the emission region is far larger than previously thought, reducing photon-photon interactions, or that new acceleration mechanisms continue operating in the afterglow phase. The MAGIC and Veritas ground-based gamma-ray telescopes have detected even higher energy photons, exceeding tera-electron volts or TeV from GRB afterglows. At these energies, each photon carries the kinetic energy of a macroscopic object, roughly equivalent to a flying mosquito compressed into a single quantum of electromagnetic radiation. The cosmological implications of gamma-ray bursts extend beyond their role as potential extinction mechanisms. Because GRBs are so luminous, they can be detected to extremely high redshifts. Corresponding to the early universe, the most distant GRB detected, GRB 090429b, occurred approximately 13 billion years ago when the universe was only 600 million years old. This burst provides a window into star formation and black hole formation in the first generation of galaxies. GRBs at high redshift probe the intergalactic medium between Earth and the burst. The gamma-ray and X-ray afterglow photons pass through intervening gas clouds, which imprint absorption lines on the spectrum. These absorption systems reveal the distribution of neutral hydrogen and heavy elements in the early universe. They show that the universe was undergoing reionization during the era when these distant GRBs occurred, with the intergalactic medium transitioning from neutral to ionized as the first galaxies formed. The jets of gamma-ray bursts also produce cosmic rays, high-energy charged particles that propagate through the galaxy at near light speed. The shock acceleration mechanisms operating in GRB jets can accelerate protons and heavier nuclei to energies exceeding 10 to the power of 20 electron volts. These ultra-high-energy cosmic rays travel across the universe, occasionally striking Earth's atmosphere and creating extensive air showers detectable by ground-based observatories like the Pierre-Auger Observatory. The origin of the highest energy cosmic rays, those exceeding 10 to the power of 19 electron volts, remains debated. Supernova remnants cannot accelerate particles to these energies. Active galactic nuclei in nearby galaxies are candidates, but the angular distribution of ultra-high energy cosmic rays does not show strong clustering toward known AGN. Gamma-ray bursts, despite being rare, release so much energy that they might contribute significantly to the ultra-high energy cosmic ray flux. This is the gamma-ray burst, a cosmic death beam born in the collapse of massive stars or the merger of neutron stars. A jet of plasma moving at 99.99% of light speed, carrying energy equivalent to 10% of the sun's mass and releasing it in 10 seconds. A searchlight that sweeps across the universe, invisible to most but lethal to any biosphere that happens to lie in its path. And 300 of them occur every single day in the observable universe. There is a hole in the universe 330 million light-years across. Not a hole in space like a black hole. Not a region of darkness that hides something. An actual absence. A volume of the cosmos that should contain approximately 2,000 galaxies, but instead contains only 60. The Boots void is not empty space between galaxies. It is empty space where galaxies should exist but do not, and no one can adequately explain why. The void was discovered in 1981 by Robert Kirshner and colleagues during a survey of galaxy redshifts. They were mapping the three-dimensional distribution of galaxies across the sky. When they noticed a region in the constellation Boots where galaxies simply stopped appearing, they expected to find a cluster or supercluster in that direction. Instead, they found nothing. The void extends from approximately 500 million to 800 million light-years from Earth, spanning an angular region larger than the full moon on the sky. The scale of this emptiness challenges cosmological models. According to the standard picture of structure formation, matter in the universe should be distributed in a cosmic web of filaments, walls, and voids. Voids are expected, but they are expected to be relatively small, perhaps 50 to 100 million light-years across. The Bootes void is 3 times larger than the largest voids predicted by simulations of structure formation. The void is not completely empty. 60 galaxies have been identified within its volume, but this represents a 97% underdensity compared to the average cosmic density. These galaxies are not randomly distributed throughout the void, but are concentrated along thin filamentary structures threading through the emptiness. They appear to be falling outward from the void center toward the denser regions surrounding it, evacuating the interior through gravitational dynamics. The physics of void formation is understood in principle. Regions that are slightly less dense than average in the early universe experience less gravitational attraction. Matter preferentially flows away from these underdense regions toward overdense regions where gravity is stronger. Over billions of years, the underdense regions become more underdense as matter continues to drain away. Small density fluctuations in the early universe are amplified by gravitational instability into the dramatic voids and filaments observed today. But the Bootes void is too large and too empty to fit comfortably within this framework. Simulations of structure formation using the standard lambda-CDM cosmological model predict the statistical distribution of void sizes. Voids as large as the Bootes void should be extremely rare, occurring perhaps once per observable universe volume. Finding one relatively nearby is statistically suspicious. Either we are lucky or the void formed through processes not captured by standard models. Alternative explanations have been proposed. Some suggest that the void formed from an unusually large underdensity in the primordial density field, a statistical fluctuation that occurred during cosmic inflation. Others propose that the void was evacuated more efficiently than normal voids, through enhanced gravitational flows driven by massive structures surrounding it. The void is bordered by several superclusters that might have gravitationally pulled matter out of the void region more efficiently than typical void environments. The most disturbing hypothesis is that the void formed through a phase transition event in the early universe. During the first fraction of a second after the Big Bang, The universe underwent several phase transitions as different fundamental forces separated from their initial unified state. If these phase transitions did not occur uniformly throughout space, they might have created regions with different vacuum energy densities. A bubble of lower vacuum energy could have expanded rapidly, creating a void as matter was pushed to the bubble walls. This mechanism would produce voids larger than expected from gravitational dynamics alone, but it would also imply that the universe's vacuum state is not uniform. Different regions might have settled into different vacuum configurations during the early universe's phase transitions. The Boots void might be a fossil of these primordial inhomogeneities, a region where the vacuum is fundamentally different from the rest of the observable universe. If true, this would have implications for the stability of the universe itself. The vacuum could be metastable, temporarily stable but not in the absolute lowest energy state. A true vacuum decay event could nucleate a bubble of lower energy vacuum that expands at light speed, converting all matter it encounters into new forms determined by the new vacuum's physics. The Boots void might be either a remnant of such an event from the early universe or a precursor to such an event in the future. The interior of the void is not merely empty, it is lonely on scales that human psychology cannot process. Imagine existing in a galaxy within the Boots void. Your telescopes would see a night sky with 97% fewer galaxies than the sky seen from Earth. The cosmic web of large-scale structure would be barely visible. You would inhabit an island universe, surrounded by darkness in all directions for 150 million light-years. Any civilization arising in such a galaxy would develop a radically different cosmology. They might not discover the expanding universe, because measuring the Hubble constant requires observing galaxies at various distances. With only 60 galaxies available across 330 million light-years, obtaining sufficient statistics would be nearly impossible. They might not discover dark matter because measuring its effects requires observing gravitational interactions in rich galaxy clusters, which do not exist in voids. Such a civilization might conclude that their galaxy is essentially the entire universe. The few distant galaxies they could observe might be interpreted as unusual nebulae within their own galaxy, or as satellite galaxies. The concept of a universe filled with billions of galaxies would never occur to them because their observational horizon contains almost no galaxies. They would be cosmologically isolated, inhabiting what appears to be a static island universe, reminiscent of pre-Hubble cosmology from the 1920s. This isolation has measurable effects on void galaxy evolution. Galaxies and voids experience fewer interactions and mergers than galaxies in dense environments. They retain more gas and continue forming stars at steady rates for longer periods. Void galaxies tend to be bluer and gas-rich compared to cluster galaxies of similar mass. The environment shapes galactic evolution through mechanisms ranging from gravitational harassment to RAM pressure stripping, and void galaxies experience minimal environmental processing. But the void's existence raises questions about cosmic structure that extend beyond galaxy evolution. The distribution of matter on the largest scales is not random. It is organized hierarchically, with galaxies clustered into groups, groups clustered into clusters, clusters forming superclusters, and superclusters forming even larger structures like walls and filaments. The Boots void represents a gap in this hierarchy at the largest scales. The void is not unique. Astronomers have discovered many large voids throughout the observable universe. The local void, approximately 60 million light-years across, lies adjacent to the local group containing the Milky Way and Andromeda. The Eridanus void spans approximately 1 billion light-years. The CMB cold spot might be associated with a supervoid along that line of sight. Voids occupy approximately 80% of the universe's volume despite containing less than 10% of its matter. This inverted universe, where emptiness dominates and matter is confined to thin filaments and walls, is the natural outcome of gravitational collapse from small initial density fluctuations. But it is deeply counterintuitive. Human experience takes place in one of the universe's rare high-density regions where matter is abundant. The typical location in the universe is not a planet orbiting a star in a galaxy. The typical location is empty space in a void, billions of light-years from the nearest galaxy. The void's interior is not merely empty of normal matter, It is also nearly empty of dark matter. Dark matter, comprising approximately 85% of all matter, follows the same gravitational dynamics as normal matter. It drains from underdense regions toward overdense regions. Voids contain dark matter at approximately 10 to 20% of the cosmic mean density. This is still far denser than the normal matter content, but it represents an extreme underdensity for dark matter. The reduced dark matter density in voids has interesting consequences. Dark matter typically provides the gravitational scaffolding around which normal matter organizes. Galaxies form within dark matter halos. The halos merge hierarchically to form larger structures. In voids, the dark matter density is so low that halo mergers become rare. Small galaxies can survive for billions of years without being accreted onto larger systems. Void galaxies are evolutionary relics, examples of galactic childhood preserved into cosmic adulthood. The void's gravitational potential is negative compared to surrounding regions. Photons climbing out of the void gain energy as they escape the negative potential, becoming blue-shifted. This effect is called the integrated Sachs-Wolf effect and should be observable in the cosmic microwave background radiation. Light from the CMB passing through voids should appear slightly cooler than light that has not traversed voids. Observations confirm this effect, providing independent evidence for the void's gravitational influence. The force pulling you toward the void's edge is real, but minuscule. Sitting on Earth, you are falling outward from several voids simultaneously, while falling inward towards several superclusters. The net effect is called the cosmic flow, or peculiar velocity relative to the Hubble flow. The local group moves at approximately 630 kilometers per second, relative to the CMB rest frame. This motion results from the gravitational pull of structures within several hundred million light-years. Part of this motion is outflow from voids, including the local void. The repulsion is not an actual force, but rather a deficit of gravitational attraction. The void contains less matter pulling you inward, so the matter outside the void dominates the net gravitational force. You are falling away from the void not because it pushes, but because it fails to pull. This gravitational asymmetry drives bulk flows that persist across hundreds of millions of light-years. The Boots void is expanding, not through cosmic expansion alone, which affects all distances uniformly. The void is expanding faster than the Hubble flow. Because matter continues to drain from its interior, the galaxies within the void are moving outward toward the void walls, accelerating under the gravitational gradient. This expansion will continue until the void merges with adjacent voids, or until cosmic acceleration driven by dark energy becomes so dominant that all structure formation ceases. In the far future, dark energy's influence will dominate over gravitational clustering. Structure formation will halt. Voids will expand indefinitely as dark energy accelerates cosmic expansion. The universe will transition from a web of filaments and voids to a collection of isolated structures, separated by exponentially growing distances. Eventually, the voids will consume everything. The matter in filaments and walls will be stretched so thin that it resembles the voids of today. The universe becomes void. This is the ultimate fate predicted by the Lambda CDM cosmological model. The cosmic web is a temporary phase in the universe's evolution. The early universe was smooth and featureless. The middle universe, which includes the current epoch, contains structure. The late universe will return to featurelessness as dark energy stretches all structures beyond causal contact. Voids like the Boots void preview this future, showing what the universe will become when emptiness dominates completely. But there is something beyond voids, something pulling on the local group, and millions of other galaxies across hundreds of millions of light-years. A concentration of mass so enormous that its gravitational influence dominates local cosmic flows. Despite being obscured behind the disk of the Milky Way, astronomers call it the Great Attractor, and no one has seen it directly. The Great Attractor was discovered through measurements of galaxy peculiar velocities. When astronomers measured the redshifts and distances of galaxies, they found systematic deviations from the smooth Hubble flow. Galaxies were flowing coherently toward a region in the constellation Centaurus approximately 200 million light-years from Earth. The implied mass concentration exceeded 10 to the power of 16 solar masses, equivalent to tens of thousands of Milky Way galaxies. The problem is that this region lies behind the zone of avoidance, the region of sky obscured by the Milky Way's disk. Dust and stars in the galactic plane absorb and scatter light from background objects, making observations difficult. For decades, the Great Attractor remained invisible. Known only through its gravitational influence, it became a cosmic ghost, pulling on everything but refusing to reveal itself. Later observations using infrared and radio wavelengths, which penetrate galactic dust more effectively, reveal that the Great Attractor corresponds to the Norma cluster, a massive concentration of galaxies hidden behind the galactic plane. But the mass of the Norma cluster is insufficient to explain the observed velocity flows. Something larger lies beyond. Further studies identified the Laniakea supercluster, a structure spanning 500 million light-years containing the mass of 100,000 Milky Way galaxies. Laniakea, meaning immeasurable heaven in Hawaiian, is the supercluster containing the Milky Way, the Virgo cluster, and the Great Attractor region. But even Laniakea is not the final answer. Beyond Laniakea lies the Shapley supercluster, the largest concentration of galaxies in the nearby universe. Shapley contains tens of thousands of galaxies and has a mass exceeding 10 to the power of 17 solar masses. It lies approximately 650 million light-years from Earth, and its gravitational influence extends across the entire local volume of the universe. You are falling toward the Shapley supercluster right now. The local group's motion includes a component directed towards Shapley at approximately 300 kilometers per second. This motion has persisted for billions of years. You have already traveled approximately 1 billion light-years through space toward Shapley, carried by the cosmic flow like a leaf in a river. The destination is certain. The local group will eventually merge with Shapley, billions of years in the future, unless dark energy accelerates cosmic expansion sufficiently to prevent the merger. The existence of structures like the Shapley supercluster and coherent flows across such vast distances challenges cosmological models. The standard model assumes that the universe becomes statistically homogeneous when averaged over scales of approximately 300 million light-years. But bulk flows persist to larger scales, suggesting that the universe's structure continues to larger scales than theoretical predictions indicate. Some cosmologists propose that these large-scale flows might be signatures of structures beyond the observable universe. If matter concentrations exist beyond the cosmic horizon, their gravitational influence could still affect matter within the observable universe. The bulk flows would represent the universe's response to gravitational gradients that extend beyond what we can directly observe. We would be falling towards something we can never see. Because it lies beyond the cosmic light horizon, this is the void and the attractor, the emptiness that should not exist at such scales, and the invisible mass pulling you. Across hundreds of millions of light-years, the universe's structure reveals itself as a battle between emptiness and concentration, between voids that expand and superclusters that collapse. And you are caught in the middle, falling simultaneously away from voids and toward attractors, your motion determined by the gravitational landscape sculpted by billions of years of cosmic evolution. "26,000 light-years from Earth, hidden behind clouds of dust so thick that visible light cannot penetrate them, the Milky Way's heart beats in X-rays and radio waves. At the center of the galaxy sits Sagittarius A star, a supermassive black hole containing 4 million solar masses compressed into a region smaller than Mercury's orbit. But the black hole is not the most dangerous aspect of the galactic center. The danger comes from what surrounds it. The central parsec of the Milky Way contains approximately 10 million stars packed into a volume that should hold only a few dozen. The stellar density exceeds the solar neighborhood density by factors of 100 million. Stars orbit so closely that their mutual gravitational interactions dominate their dynamics. They collide. They are tidally disrupted. They are flung outward at velocities exceeding 1,000 kilometers per second. The galactic center is a gravitational furnace where stellar encounters that would be impossibly rare elsewhere occur routinely. The nearest star to Earth, Proxima Centauri, orbits approximately 4 light-years away. In the galactic center, the nearest stars orbit at distances measured in light hours. The night sky seen from a planet in the galactic center would contain no darkness. Stars would be separated by angular distances smaller than the full moon. The sky would glow with continuous starlight from millions of stars, each individually resolvable. The integrated starlight would be bright enough to read by at midnight. But you would not survive to read. The radiation environment in the galactic center is lethal. Massive stars form at enhanced rates in the dense gas clouds surrounding Sagittarius A star. These stars live brief lives, perhaps 3 to 10 million years, before exploding as supernovae. The supernova rate in the central parsec is approximately 1 per few thousand years. Far higher than the rate in the solar neighborhood, each supernova bathes the region in X-rays and gamma rays, ionizing the interstellar medium and creating shockwaves that propagate through the crowded stellar population. The supernova remnants overlap. One supernova's expanding shockwave collides with the remnants of previous supernovae, creating a hot bubble of plasma at temperatures exceeding 10 million degrees Celsius. This hot plasma fills the interstellar medium between stars, emitting thermal X-rays. The X-ray flux in the galactic center exceeds the solar neighborhood flux by factors of thousands. Any planet orbiting a star in this environment would have its atmosphere stripped away by the intense radiation field. Sagittarius A star itself emits relatively little radiation currently because it is not actively feeding. The black hole is essentially dormant, accreting matters at only approximately 1/10,000th of the Eddington rate. But this quiescence is temporary. Observations reveal clouds of gas orbiting near the black hole, some on trajectories that will bring them close to the event horizon. When these clouds are tidally disrupted and accreted, Sagittarius A star will flare, temporarily increasing its luminosity by factors of hundreds or thousands. One such cloud, designated G2, made a close approach to Sagittarius A star in 2014. Astronomers predicted that the tidal forces would tear the cloud apart, sending its material into the accretion disk and triggering a flare visible across the electromagnetic spectrum. The observations revealed something unexpected. The cloud survived the encounter relatively intact, suggesting it might be the stripped outer envelope of a star rather than a diffuse gas cloud. The star, if it exists, orbits within 400 AU of the black hole, closer than the Kuiper Belt's distance from the Sun. A star orbiting that close to a 4 million solar mass black hole experiences tidal forces sufficient to distort its shape. The star becomes elongated, stretched toward the black hole by the differential gravity between its near and far sides. As it orbits, the star is alternately compressed and stretched by varying tidal forces. This tidal pumping heats the stellar interior, potentially triggering enhanced nuclear fusion or even nova-like eruptions. The star is being slowly destroyed by its proximity to the black hole, shedding mass with each orbit. But stellar encounters with Sagittarius A star can be far more catastrophic. Approximately every 10 to 100,000 years, a star passes close enough to be tidally disrupted completely. The tidal disruption event, or TDE, occurs when the star crosses the tidal disruption radius, the distance where tidal forces exceed the star's self-gravity. For a solar-type star encountering a 4 million solar mass black hole, the disruption radius is approximately 100 million kilometers, roughly half the Earth-Sun distance. At this distance, the star is ripped apart. The process occurs over hours as the tidal forces overcome the star's internal structure. The star does not explode. It unravels like a ball of yarn being pulled apart. Stellar material streams toward the black hole in a coherent strand, while other material is flung outward at velocities exceeding 1,000 kilometers per second. Approximately half the stellar mass falls toward the black hole. The other half escapes on hyperbolic trajectories, destined to wander through the galaxy forever. The accreting material forms an accretion disk that brightens dramatically over days to weeks. The accretion rate temporarily exceeds the Eddington limit by factors of hundreds. The inner accretion disk heats to temperatures exceeding 100 million degrees, emitting X-rays and ultraviolet radiation at luminosities approaching 10 to the power of 39 watts. For weeks or months, Sagittarius A star becomes the brightest X-ray source in the galaxy, visible to X-ray telescopes anywhere in the Milky Way. The tidal disruption also launches jets. The rapidly rotating accretion disk generated by the infalling stellar material can drive relativistic jets through the Blandford-Znajek mechanism. These jets, though short-lived compared to jets from actively accreting supermassive black holes, still carry enormous energy. They propagate outward through the galactic center, shocking and heating the surrounding medium. Any star or planet in the jet's path would be irradiated by intense gamma-ray flux. The stellar population in the galactic center is itself bizarre. Normal main sequence stars exist there, but they are outnumbered by exotic stellar types. The S-stars, a population of approximately 100 young massive stars, orbit Sagittarius A star at distances ranging from light hours to light weeks. These stars formed within the last few million years, despite the fact that star formation at such close proximity to a supermassive black hole should be impossible. The intense tidal forces and radiation field should prevent molecular clouds from collapsing. One hypothesis proposes that the S-stars formed farther from the black hole and migrated inward through dynamical friction, losing orbital energy to interactions with other stars and dark matter. Another hypothesis suggests they formed in a massive accretion disk around Sagittarius A star during a recent feeding episode. This disk would have been gravitationally stable enough to fragment into stars despite the tidal environment. Both scenarios imply recent dramatic events in the galactic center's history. The star S2, also designated S02, has an orbital period of approximately 16 years and a closest approach distance of approximately 17 light hours from Sagittarius A star. At closest approach, S2 reaches velocities exceeding 5,000 kilometers per second, approximately 2% of light speed. General relativistic effects become measurable at these velocities. The star's orbit precesses, meaning its orientation rotates over time. The precession rate, approximately 12 arc-minutes per century, matches general relativity predictions and rules out alternative theories of gravity. But S2 is not the closest star. S62 holds that distinction with the closest approach of approximately 16 light hours and an orbital period of 9.9 years. At closest approach, S62 reaches velocities exceeding 8% of light speed. The star experiences time dilation measurable by comparing its observed spectrum to laboratory spectra. The star's own clock runs approximately 0.1% slower than clocks in the solar neighborhood during its close approach. The region immediately surrounding Sagittarius A star, within approximately 1 light year, should be nearly empty of stars according to standard stellar dynamics. Two-body gravitational interactions between stars cause their orbits to evolve over time. Some stars gain energy and are ejected outward. Other stars lose energy and sink inward toward the black hole. This mass segregation process should create a cusp in the stellar density profile. With density increasing steeply toward the black hole, observations reveal the opposite. The stellar density appears nearly constant or even slightly decreasing towards Sagittarius A star within 1 parsec. This discrepancy is called the missing cusp problem. Several explanations have been proposed. Intermediate mass black holes, ranging from hundreds to thousands of solar masses, might orbit within the central parsec. Their gravitational influence would dynamically heat the stellar population, preventing cusp formation. Alternatively, recent star formation or black hole growth might have disrupted a previously existing cusp. The galactic center also contains an unusual concentration of pulsars. Over 100 millisecond pulsars have been detected within 30 parsecs of Sagittarius A star. These are old, recycled pulsars that have been spun up to rapid rotation by accreting matter from companion stars. The millisecond pulsars in the galactic center have traveled there from elsewhere in the galaxy, sinking to the center through dynamical friction. They represent the endpoint of stellar dynamical evolution, the stellar corpses that reach the galaxy's gravitational pit. These pulsars provide laboratories for testing general relativity in strong gravitational fields. A pulsar in a close orbit around Sagittarius A star would experience frame dragging from the black hole's rotation. Its pulses would be delayed by varying amounts as its radio waves propagate through the curved spacetime near the black hole. Observing such effects would measure the black hole's spin directly, one of the fundamental parameters characterizing the black hole. But no pulsar has been found in a very close orbit around Sagittarius A star. The absence might be observational, resulting from scattering of radio waves by the turbulent plasma near the black hole. That obscures pulsars behind a screen of ionized material. Or it might be real, indicating that pulsars are destroyed or ejected before reaching the innermost orbits. A pulsar passing close to Sagittarius A star would experience tidal forces sufficient to distort the neutron star itself, potentially triggering instabilities or magnetic field reconnection events. Beyond the immediate vicinity of the black hole lies the central molecular zone, a concentration of dense molecular gas spanning approximately 1,500 light-years. This gas, primarily molecular hydrogen with traces of carbon monoxide and other molecules, contains approximately 10% of the Milky Way's total molecular gas. Despite occupying less than 1% of the galactic disk area, the gas clouds are turbulent, with velocity dispersions exceeding 50 kilometers per second, far higher than in typical molecular clouds. The turbulence is driven by supernovae, stellar winds from massive stars, and interactions with the galactic bar, an elongated stellar structure that funnels gas inward toward the galactic center. The gas clouds collide and compress, triggering star formation. But the star formation efficiency, the fraction of gas converted to stars per unit time, is surprisingly low. The galactic center should be forming stars at rates hundreds of times higher than observed. The suppression of star formation might result from the intense radiation field that heats and ionizes gas, preventing gravitational collapse. Or it might result from turbulence that prevents gas from settling into cold, dense configurations suitable for collapse. Or magnetic fields threading the clouds might provide additional pressure support that resists collapse. The galactic center's extreme environment creates conditions for star formation vastly different from the solar neighborhood. The Fermi bubbles represent another mysterious feature emanating from the galactic center. These are giant lobes of gamma-ray emitting plasma extending approximately 25,000 light-years above and below the galactic plane. They were discovered in 2010 by the Fermi Gamma-Ray Space Telescope. The bubbles have sharp edges and a relatively uniform gamma-ray spectrum, suggesting they formed from a single explosive event or sustained energy injection over millions of years. One hypothesis proposes that the bubbles formed from a recent episode of intense activity by Sagittarius A star. If the black hole accreted large amounts of matter within the last few million years, the resulting winds and jets would have inflated the bubbles. The required energy input, approximately 10 to the power of 56 joules, equals the rest mass energy of 10,000 solar masses. This is plausible given that Sagittarius A star currently accretes at rates far below its potential and likely experienced much higher accretion rates in the recent past. An alternative hypothesis invokes intense starburst activity in the galactic center. If star formation proceeded at rates 100 times higher than currently observed for approximately 10 million years, the integrated supernova and stellar wind energy output would be sufficient to inflate the Fermi bubbles. The bubbles would be galactic-scale superbubbles, analogous to superbubbles observed in starburst galaxies but scaled up to match the Milky Way's central black hole mass. The true nature of the Fermi bubbles remains uncertain, but they demonstrate that the galactic center is capable of launching energetic outflows that affect the entire galaxy. These outflows carry heavy elements synthesized in stars, distributing them throughout the galactic halo. They also carry magnetic fields and cosmic rays that influence star formation in the galactic disk. The galactic center does not simply absorb matter through its black hole. It also ejects matter and energy that shape galactic evolution. You orbit within the gravitational influence of this system. The Sun completes one orbit around the galactic center every 230 million years. At a distance of approximately 26,000 light-years, the orbital velocity is approximately 220 kilometers per second. You are gravitationally bound to Sagittarius A star, just as Earth is gravitationally bound to the Sun. The black hole's gravity reaches out across the entire galaxy, binding hundreds of billions of stars into a rotating disk. But the orbit is not perfectly circular. The Sun oscillates above and below the galactic plane with a period of approximately 30 million years. Currently, the Sun is approximately 27 light-years above the galactic midplane and moving upward at approximately 7 kilometers per second. In approximately 14 million years, the Sun will reach its maximum height of approximately 250 light-years above the plane before falling back through the disk. Each passage through the galactic plane exposes the solar system to enhanced cosmic ray flux, increased comet impacts from gravitational perturbations of the Oort cloud, and potential close encounters with molecular clouds. Some paleontologists have proposed that the solar system's oscillations through the galactic plane correlate with mass extinctions on Earth. A hypothesis called the Shiva hypothesis. The evidence remains controversial, but the 26 to 30 million year periodicity of some extinction events matches the vertical oscillation period suspiciously well. This is the galactic center, a supermassive black hole surrounded by millions of stars packed into a space that should be nearly empty. A region where stars collide and are torn apart by tides, where supernovae explode every few thousand years, where the radiation field would sterilize any planet, where space-time itself is curved so severely that clocks run slower and orbits precess measurably, and you are falling toward it, carried by the Sun's orbit around this gravitational and electromagnetic hell. The vacuum of space is not empty. It seethes with quantum fields that permeate every point in the universe. These fields exist in a particular energy state called the vacuum state. But here is the terrifying part. The vacuum state we inhabit might not be the lowest possible energy state. We might be living in what physicists call a false vacuum, a metastable configuration that could decay at any moment into the true vacuum. And if that decay begins, it will propagate outward at the speed of light, destroying everything in its path. You cannot run from it. You cannot shield against it. You will not see it coming. The concept emerges from quantum field theory, the mathematical framework describing how fundamental particles and forces operate. In quantum field theory, the vacuum is not merely the absence of particles. It is the lowest energy state of all quantum fields. The Higgs field, discovered in 2012 at the Large Hadron Collider, has a vacuum expectation value of approximately 246 giga-electron-volts. This value determines the masses of fundamental particles through their interactions with the Higgs field. But calculations based on the standard model of particle physics and the measured Higgs mass of 125 giga-electron-volts suggest something unsettling. The Higgs potential, the function describing the field's energy as a function of field value, appears to have two minima. One minimum corresponds to our current vacuum with the Higgs field at 246 GeV, but at much higher field values, approximately 10 to the power of 17 GeV. The potential might have a deeper minimum. If this second minimum exists and is indeed lower in energy than our current vacuum, then our universe exists in a false vacuum. The true vacuum, the absolute lowest energy state, corresponds to the second minimum where the Higgs field has a much higher value. Transitioning to this true vacuum would be energetically favorable. The universe wants to decay. It is being prevented only by a quantum mechanical barrier, an energy hill that the field must tunnel through to reach the lower state. Quantum tunneling allows particles and fields to transition through energy barriers that would be classically forbidden. An electron can tunnel through a potential barrier even though it lacks sufficient energy to climb over it classically. The probability of tunneling depends exponentially on the barrier height and width for the Higgs field to tunnel from the false vacuum to the true vacuum. A bubble of true vacuum must spontaneously nucleate somewhere in the universe through quantum fluctuations. The nucleation rate is extraordinarily low if the barrier is high. Calculations suggest that the probability of a dangerous vacuum bubble nucleating in any given cubic kilometer of space during the age of the universe is negligibly small, far less than 10 to the power of -100. The universe appears stable on timescales vastly exceeding its current age. But the probability is not zero, and the universe is large, with approximately 10 to the power of 80 protons in the observable universe, occupying a volume of approximately 10 to the power of 80 cubic meters. Even extremely low probabilities become relevant when multiplied by such enormous numbers. Once a bubble of true vacuum nucleates, it expands at the speed of light. The bubble wall is a region of space where the Higgs field rapidly transitions. From the false vacuum value to the true vacuum value, this transition releases the difference in vacuum energy densities. The energy release is approximately 10 to the power of 80 joules per cubic meter, comparable to nuclear energy densities. The expanding bubble wall is essentially a detonation wave, propagating through the fabric of space-time itself. Everything inside the bubble is destroyed, not merely killed or disassembled, fundamentally transformed. The Higgs field value inside the bubble is different from outside. This means particle masses are different inside the bubble. Quarks and electrons have different masses determined by their coupling to the altered Higgs field. Atoms cannot exist in their current configurations. Because atomic structure depends on the mass ratio between electrons and nuclei, chemistry ceases. Nuclear physics changes. The fundamental constants that govern matter's behavior are no longer constant. The bubble wall arrives at light speed. You receive no warning. Light from the approaching wall cannot reach you faster than the wall itself. One moment you exist in normal spacetime. The next moment, the wall passes through you. Your atoms disintegrate as their constituent particles acquire new masses. Incompatible with atomic stability, the electromagnetic forces binding electrons to nuclei change. The nuclear forces binding quarks into protons and neutrons change. Matter as we know it cannot exist in the true vacuum. It is replaced by whatever matter configurations are stable under the new physics. The bubble wall is only approximately 1 nanometer thick, the distance over which the Higgs field transitions between vacuum states. As the wall passes through Earth, the planet does not explode dramatically. It simply stops being Earth. The constituent particles are still there, but they have been transformed into exotic forms of matter with masses and interaction strengths determined by the true vacuum's physics. These new forms of matter would not coalesce into planets or stars or any structure recognizable as matter from the false vacuum perspective. The energy released at the bubble wall drives its expansion. The wall accelerates outward through space, its velocity approaching the speed of light asymptotically. The bubble interior is causally disconnected from the exterior. Light emitted from inside the bubble cannot escape because the expansion velocity equals light speed at the wall. An external observer watching a vacuum decay bubble form would see a spherical region that suddenly goes dark. The sphere expands at light speed, erasing everything it contacts from the observable universe. But the description from the external observer's perspective is misleading, because it suggests time continues normally outside the bubble. In reality, the true vacuum has a different cosmological constant than the false vacuum. The cosmological constant determines dark energy density, which drives cosmic expansion. If the true vacuum has a higher cosmological constant, the universe inside the bubble undergoes accelerated expansion far more rapid than the current dark energy-driven acceleration. Space expands so quickly that any matter inside the bubble is immediately diluted to negligible density. Alternatively, if the true vacuum has a negative cosmological constant, the bubble interior undergoes catastrophic collapse. Instead of expanding infinitely, space inside the bubble begins contracting. Any matter or energy inside falls toward the bubble center. Under the influence of the negative energy density, the interior collapses into a singularity, a big crunch occurring within the bubble while the rest of the universe continues its normal expansion. The bubble wall expands outward, consuming more of the universe and adding it to the collapsing interior. The vacuum decay catastrophe is sometimes called the ultimate ecological disaster. It is the only known physical process that can destroy the entire universe. Supernova destroy star systems. Gamma-ray bursts sterilize large regions of galaxies. Even supermassive black hole mergers affect only their immediate cosmic neighborhoods. But vacuum decay, once initiated, is unstoppable and unlimited. The bubble expands forever, eventually consuming the entire observable universe and everything beyond it. There is no refuge, no shelter, no way to survive. The possibility of vacuum decay has been discussed since the 1970s when Sidney Coleman and Frank DeLucia developed the mathematical framework for analyzing tunneling between vacuum states in quantum field theory. Their work demonstrated that false vacuum decay is inevitable given sufficient time if a lower energy vacuum state exists. The question is not whether decay will occur, but when and where it nucleates. Recent measurements of the Higgs boson mass and the top quark mass, combined with precision calculations of the Standard Model at high energies, have refined estimates of vacuum stability. The results are ambiguous. The current vacuum appears to be either metastable, with a decay time far exceeding the universe's age, or absolutely stable, depending on precisely how the Higgs field behaves at energy scales beyond current experimental reach. The uncertainty arises because extrapolating the Standard Model to energies of 10 to the power of 17 GeV requires assuming no new physics intervenes at intermediate energies. If new particles or forces exist at energies between the electroweak scale, approximately 100 GeV, and the Planck scale, approximately 10 to the power of 19 GeV, they could modify the Higgs potential significantly. Supersymmetry, if it exists, would stabilize the vacuum by introducing new particles that contribute to the Higgs potential in ways that raise the barrier height or eliminate the second minimum entirely. The non-observation of supersymmetric particles at the Large Hadron Collider suggests that if supersymmetry exists, it is broken at energy scales higher than accessible by current accelerators. The metastability of the vacuum also depends on gravitational effects. During cosmic inflation, the Higgs field might have been displaced far from its current value by quantum fluctuations, amplified to macroscopic scales. If the Higgs field reached values near the second minimum during inflation, it would have immediately decayed to the true vacuum. The fact that we exist in the false vacuum implies either that the Higgs field never reached dangerous values during inflation, or that the true vacuum minimum does not actually exist. Some physicists interpret the apparent vacuum metastability as evidence for the anthropic principle. If the vacuum were absolutely stable, the universe might have settled into the true vacuum during its early evolution. The true vacuum's physics might not allow the formation of atoms, molecules, stars, planets, or life. The fact that we observe ourselves in a metastable vacuum might simply be selection bias. Only in metastable vacuums can observers evolve to ask questions about vacuum stability. But there is another terrifying possibility. Vacuum decay might have already begun somewhere in the universe. If a bubble nucleated sufficiently far from Earth, beyond the cosmic horizon approximately 46 billion light-years away, the bubble wall has not reached us yet. It is propagating toward us at light speed but requires tens of billions of years to cross the intervening distance. We would have no way to detect the approaching catastrophe. We cannot see beyond the cosmic horizon. We cannot receive signals from regions that are too distant for light to have reached us since the Big Bang. The bubble might have nucleated 1 billion light-years away 1 billion years ago. The wall is now approximately halfway to Earth, having consumed hundreds of millions of galaxies. But we see nothing. The light from the bubble interior cannot escape through the light-speed expanding wall. We observe the galaxies in that direction as they were 1 billion years ago. Still in the false vacuum, unaware of their impending destruction, in approximately 1 billion years, the wall will arrive here. Every galaxy between Earth and the nucleation point will be erased from existence. Then it will be our turn. There is no defense. No technology can prevent vacuum decay or shield against its effects. The bubble wall operates at the most fundamental level of physical law, rewriting the rules that govern matter and energy. Any conceivable defense mechanism would itself be composed of matter obeying the false vacuum's physics. When the true vacuum arrives, the defense mechanisms cease to function because their constituent atoms dissolve into exotic particles under the new physics. The only way to survive vacuum decay would be to not exist in the false vacuum in the first place. If advanced civilizations develop the technology to create artificial universes with designer physical laws, they might evacuate into those pocket universes before vacuum decay arrives. But creating universes requires manipulating spacetime at the Planck scale, far beyond any conceivable technology. It requires energy densities approaching 10 to the power of 113 joules per cubic meter, the Planck energy density. No known physical process, except the Big Bang itself, achieves such conditions. Some theoretical physicists have proposed that sufficiently advanced civilizations might trigger vacuum decay deliberately, either accidentally through high-energy experiments or intentionally as a form of cosmic engineering or warfare. The Large Hadron Collider raised concerns about triggering vacuum decay or creating dangerous microscopic black holes. Detailed calculations demonstrated that the collision energies achieved at the LHC, approximately 14 tera-electron volts, are far too low to meaningfully perturb the Higgs field or nucleate vacuum decay bubbles. Cosmic rays strike Earth's atmosphere at energies exceeding 10 to the power of 20 electron volts. If such energies could trigger vacuum decay, Earth would have been destroyed billions of years ago. But there might exist energy regimes where vacuum decay becomes probable. Planck-scale particle colliders, if they could be built, would probe physics at the absolute limit of quantum field theory's validity. At these energies, space-time itself becomes uncertain. Quantum fluctuations in the metric of space-time create a foamy structure where the concepts of distance and time break down. Collisions at Planck energies might nucleate vacuum decay bubbles or create other exotic objects like baby universes or wormholes. No civilization will build Planck-scale accelerators accidentally. The energy required exceeds the total energy output of stars. But in the far future, civilizations powered by Dyson spheres or Penrose process energy extraction from black holes might achieve such capabilities. They would face an ethical dilemma. Probing Planck-scale physics could unlock understanding of quantum gravity and allow manipulation of space-time. But it also risks triggering vacuum decay that destroys not just the experimental apparatus but the entire universe. How much knowledge is worth the risk of omnicide? This is vacuum decay. The possibility that the universe exists in a metastable state that could collapse at any moment into a configuration where atoms cannot exist. A catastrophe that propagates at light speed, impossible to predict, impossible to prevent, impossible to survive. A reminder that the stability of matter, the constancy of physical law, and the very possibility of existence might be temporary accidents of cosmic evolution. And somewhere in the universe right now, a bubble of true vacuum might be expanding toward Earth, erasing everything in its path, arriving in 10 billion years or 10 billion seconds, moving at light speed through the darkness. You have traveled through the universe's execution chambers. You have seen surfaces where matter forgets how to be solid. Atmospheres hotter than their own stars. Regions where time stops and space curves back on itself. Voids that should not exist. Beams that burn through galaxies. And the possibility that reality itself is temporary, waiting for a quantum fluctuation to erase everything at light speed. But here's what you need to understand. These are not distant abstractions relegated to the deep cosmos, safely separated from your existence by billions of light years and billions of years of time. These horrors operate on human timescales in cosmic neighborhoods measured in thousands, not billions, of light years. You are surrounded. You are already inside several of these killing grounds. And the only thing protecting you is luck and distance, both of which are temporary. The Sun will produce another Carrington-class coronal mass ejection. The statistics are certain. The timing is not. It could happen tomorrow. It could saturate Earth's magnetosphere with enough energy to collapse electrical grids across entire continents. The transformers would fail. The power would die. And in the cascading infrastructure collapse that follows, civilization would have weeks to months before the systems sustaining 8 billion humans begin failing permanently. The corona does not care about your technology or your preparedness. It operates according to magnetic instabilities driven by convection patterns 30,000 kilometers below the visible surface. The magnetar population in the Milky Way numbers in the tens of millions. Most are dormant. Some are active. Every few decades, one experiences a giant flare. That releases more energy in 1/10 of a second than the Sun emits in 100,000 years. SGR 1806-20 is 50,000 light-years away. That distance saved Earth from its 2004 giant flare. But there are closer magnetars. SGR 0526-66 is only 13,000 light-years distant. It has flared before, it will flare again, and if the next giant flare is oriented toward Earth, the gamma-ray flux will strip the ozone layer in hours. You orbit inside an accretion disk, not around a black hole, around the galaxy. The galactic disk is thin, approximately 1,000 light-years thick. And the Sun passes through the midplane every 30 million years. Each passage exposes the solar system to enhanced cosmic ray flux, molecular cloud encounters, and gravitational perturbations that send comets from the Oort cloud plunging toward the inner solar system. The fossil record shows mass extinctions occurring with periodicities that match the vertical oscillation periods suspiciously well. The Sun is currently 27 light-years above the midplane and rising. In 14 million years, you will reach maximum height before falling back through. The galaxy is patient. The disk does not forget. Sagittarius A star will eventually wake up. Supermassive black holes do not remain dormant forever. The gas clouds orbiting within light hours of the event horizon will eventually be disrupted. The material will fall into the accretion disk. The black hole will flare. For months or years, the galactic center will blaze in X-rays bright enough to be detected by instruments throughout the galaxy. The radiation will not reach Earth at lethal intensities across 26,000 light-years, but it will be a reminder. The heart of the galaxy is a 4 million solar mass monster that occasionally feeds, and you are gravitationally bound to it, completing an orbit every 230 million years. The gamma-ray burst threat is statistical. The galaxy experiences long-duration GRBs approximately once every few 100,000 years. The jet opening angles are approximately 5 degrees. The probability that a Milky Way GRB points toward Earth is approximately 1 in 1,000. This gives a lethal GRB approximately once every few 100 million years. The Ordovician extinction occurred 445 million years ago. The Devonian extinction occurred 375 million years ago. The Permian extinction occurred 252 million years ago. The pattern is not random. The galaxy has been shooting at Earth for billions of years. Most shots miss. Some hit. The Boötes void is expanding. All voids are expanding. Matter continues draining from their interiors toward the filaments and walls surrounding them. In billions of years, the voids will dominate. Dark energy will stretch space so rapidly that structure formation ceases entirely. The universe will transition from a cosmic web of filaments and voids to a collection of isolated structures separated by distances that light cannot cross in the remaining lifetime of the universe. Everything will become void. The matter will still exist, but it will be so diluted that the average density approaches zero. The universe becomes empty, not through destruction, through dilution. And beneath all of this, beneath every structure and every threat and every physical process, the vacuum seethes. The quantum fields permeating space exist in a state that might be metastable. The calculations are uncertain. The measurements are imprecise. But the possibility remains that the universe is fundamentally unstable, waiting for a quantum fluctuation to trigger collapse into the true vacuum. If the bubble has already nucleated beyond the cosmic horizon, the wall approaches at light speed. You will never see it coming. You will never detect it. The last sensation any conscious being in the universe will experience is the present moment. Then the bubble wall arrives, then physics changes, then everything ends. This is not science fiction. This is inventory, a catalog of physical processes operating in the universe right now according to laws verified by observation and experiment. The magnetars exist. The black holes exist. The voids exist. The false vacuum hypothesis is consistent with measured particle masses and quantum field theory calculations. These are not threats that might emerge from future technological development or alien invasion. These are threats embedded in the structure of physical law itself. Operating continuously, waiting for the right conditions or the right moment to sterilize or destroy or fundamentally transform everything. You cannot build shelters against vacuum decay. You cannot evacuate Earth to escape galactic threats operating on scales of thousands of light-years. You cannot negotiate with the corona or plea bargain with magnetars. These processes do not care about human existence or human values or human survival. They operate according to physics. They will continue operating after humanity is extinct. They will continue operating after Earth is destroyed. They will continue operating after the sun dies. They are the universe expressing its fundamental character, which is violence on scales that obliterate meaning. The universe is not hostile to life. Hostility implies intent. The universe is indifferent. It contains regions where life can temporarily exist, because the physics happens to allow molecular chemistry and liquid water and stable energy sources. But these regions are tiny oases in a cosmic desert of radiation, vacuum, gravitational violence, and quantum uncertainty. The typical location in the universe is not a planet. The typical location is the interior of a void, billions of light years from the nearest star, where the temperature is 3 degrees above absolute zero and the density is 1 hydrogen atom per cubic meter. Earth is an anomaly. Life is an anomaly. Consciousness is an anomaly. And anomalies are temporary. But you are here now, in this moment, in this improbable configuration of matter that allows neurons to fire and thoughts to form and awareness to briefly illuminate a fragment of space-time before the darkness returns. You are a pattern in matter complex enough to recognize its own existence, and terrified enough to realize its own fragility. You are surrounded by cosmic horrors operating on scales you cannot escape. But for this moment, the sun's coronal mass ejection is pointed away from Earth. The magnetar flares are aimed in other directions. The gamma-ray burst jets miss. The vacuum does not decay. And you continue existing. This is the universe's gift. Not safety, not protection, not meaning. Just temporary existence in a cosmos that permits complexity for brief intervals. Before returning everything to simplicity, you are made of atoms forged in stellar cores and scattered by supernovae. You are made of matter that has survived billions of years of cosmic violence to temporarily assemble into a configuration capable of reading these words. And when the violence finally reaches you, whether through solar storms or stellar death or vacuum collapse, those atoms will scatter again and continue their journey through the cosmos. If this exploration of cosmic horror has expanded your understanding of the universe's true nature, hit that like button. Subscribe to this channel for more investigations into what the cosmos keeps hidden in plain sight. Because the universe is not finished revealing its terrors. Every new discovery, every new observation, every deeper look into the cosmic abyss reveals processes more extreme and more violent than the previous generation imagined possible. The inventory of cosmic horrors grows with each passing year. And you are here, watching, learning, waiting. The universe is terrifying, and it does not care that you are terrified.